Okay, I'm going to talk about this simulation, so sim to real, which is basically problems of translation between the simulations and reality, or back and forth, where you train your robots in simulations, and then how you transfer to a real reality. That's kind of the main topic of my talk. The talk itself a little bit more specific, and specific to the challenge. So my background is in computer graphics in general. I did real-time games, computer graphics, stuff like that. I did some physics, but I'm not an expert actually in physics. Yeah. So let's basically, what do you think? What are the challenges? One challenge is obviously very simple. Everyone will be able to say that the physics simulation is imperfect, right? So there'll be difference always between the simulation in the physical engine and the real world. But what are other problems that you can come up with? Other challenges. It's not just with physics.
Complexity computation is very computation consuming.
Yeah, it is computation consuming, but we don't care about that nowadays, right? Ask someone for the cloud server, and that's it. Oh, but it's a good problem. What else?
Very common problem is not modeling latency properly. Latency, sensor latency, processing latency, actuation latency. Not
Interesting.
modeling it properly in your simulation.
So I haven't even added that. That's a very good point. The latency is a very tough to simulate, but it kind of boils down to sensors and sensor imperfection in general, right?
Yeah.
That it's both latency that we get from the sensor. Latency is different in real world and different in simulation. The sensors might be in simulation will be imperfect. The sensor itself can be imperfect, but when we render it, when we try to simulate the sensor, usually it will not look like real world for multiple reasons. One reason is, of course, that our rendering is not as real like reality, right? But as well, we need to acquire some data in order to do that simulation. And always, quite often, the data will be not perfect. And that will, the data imperfection will affect both physical simulation, but it will affect how our sensors simulation work. What else can you think of?
In the model. Well, sorry. Thinking from a robotics perspective, the mechanical model.
Yes. Yeah, the mechanical model itself will be quite simplified, right? That's we still cannot come close to the complexity of robotic hands. But one other problem, which is people don't often mention, is actually how do we integrate the reasoning part? How do the brain of the robot? How do we integrate that into the simulation? Because quite often it's some other hardware, maybe like neuromorphic, or it can be some just Python code or whatever. It quite often it's not part of the simulation, and it will be running. It will be imperfect data, right? Even if we simulate that reasoning, and obviously it will the reasoning itself will be quite different in the simulation. So that's kind of quite often problem. How do we put the reasoning part into the simulation? And of course, kind of the last big problem is just the real world has a lot of noise, and the same noise that the imperfections that we have in simulation, right, both in physical and sensors, we will have the same kind of type of problem that the noise will affect our real actuators, real sensors. When we move something, the actuation will be not as strong as in reality or other way around. It's hard to match that. Anyway, I want to talk next is about the physics engines and how they work inside. I don't know if you know about them. I imagine that you approximately know how they would work inside, right? But I want to kind of go on a high level overview of what is happening in a physics engine during the simulation. And in general, we have a bunch of physics engines that are pretty stable, pretty good quality, and they kind of solve different problems, and you can pick and match. But if MuJoCo is probably the most known in robotics, it's quite precise. It has pretty decent speed, and then there's a Dart and Drake, which is much slower than MuJoCo, but it's much more precise in simulation. Then we have two engines that came actually from the gains from graphics, and they just were incrementally improved until they started supporting the pretty good simulation and the robotic level of simulation. NVIDIA made a lot of effort with the physics and Havoc. So they are both fast. They support GPUs, maybe not as precise as DAR. And then there are some new types of physical engines which are differentiable. They are kind of built on top of JAX. This is DRAX specifically. It's built on top of JAX, but you can imagine you can build something like that on top of PyTorch. So the kind of upsides of those differentiable engines, apart that they're differentiable, that they emit just out of by the fact that they use, yes,
Go ahead.
by the fact that they use PyTorch or JAX, they are GPU accelerated by default. So you don't need to, other people have to do a lot of work with so the CPU kind of optimized physical engines into GPU. But Rux, it's like by the virtue of itself, it works from GPU.
I have to make a comment here. I have to say that, when we do real robotics, like in a cart pull, we're still using basic ODE simulation. ODE, we understand the physics of this cart pull. We understand the ODE, we understand the parameters in there. We don't need some fancy simulation engine. You just need an ODE time stepper. And for the car, we rely very deeply on these TU unit car models, which were developed over many years. They are verified in real hardware. Most of these engines are developed by machine learning people that never actually touch a real robot. 99% of the time, this is all pure simulation. Transferring this to reality is a whole different story, as far as I know.
Yeah, of course. It's Brux, but which is developed by machine learning people. Other are developed more by like the physics. They actually have quite a lot of robot people with the robotic experience. And there's a bunch of like Bullet, for instance, it comes with the KUKA support. Like there is a lot of like built-in support for those engines nowadays. But it is, you're absolutely right for this.
That's probably well developed, yeah.
For simple problems, you rather probably want the custom engine. And like the automotive people, they as well, they have the build, they don't sometimes on top of the engine, sometimes right in their own.
When you say ODE, you mean the
Oh, sorry, that's a old.
yeah,
No, that's actually a package. It's a
open dynamics engine. Yeah.
But yeah, it's just
Could you quickly state what you understand by physics engine? Because in my mind, I'm a circuit guy.
yeah.
So when somebody talks to me physical simulation, I'm thinking of a device level, atomistic level simulation.
Yes, okay. I will talk maybe next about that, but it's kind of this very simple object dynamics, like a.
But that's ODE. So.
Yes, ODE. Yes, it's only ODE. There's nothing. There's no quantum level simulations. There are no heat simulations. There's nothing like that. It's not stochastic. It's stochastic because how it is calculated, but it is not stochastic by there is no stochastical element when the simulation happens. No, it's side effect of the noise computation. But yeah, it's kind of school level physics, which
Newton's law.
Yeah, Newton.
Basically.
Yes, exactly. Nothing. Newton and Euler. It's like a joke video here. I'm not sure why it's not working, but it's a bit of a joke, right? It's like how these physics engines compare between each other, right? So different levels. How much can you simulate, right? For instance, here you can see that the object is kind of moving, but it does not flip precisely. It's kind of a joke. You can have different levels of simulation, and you can pick whatever you want, and they will have different performance characteristics and quality. So what does that physics engine actually do? So as we spoke, it does body dynamics, which is kind of very simple Newtonian transformation and Euler kind of rotation. That's it. It's very easy. It's differentiable and quite like anyone can write that code, right? The next part of it is actually collision detection. So once the object moves, right, they tend to overlap each other, collide each other. So we have to solve that problem. And collision detection basically will feed into the last step of the physical engine. So basically, you can think about the physical simulation as these 4 steps, rough 4 steps. The first is the body dynamics, how bodies move. The second one is this: once they collide, how do we resolve this collision? Then there are various joints, springs, actuators, all that basically feeds into the constraints. So both collisions and friction and joints, they all create certain types of constraints. And those constraints will be solved inside the solver. So that's a very, very high level what the physics engine is doing. So the first is body dynamics. Yeah, we usually, most of the engines use discrete time step. So you can see this ball kind of jumping, although visually you probably wouldn't see that in animation, but in reality, it's like a very discrete time steps. As I said, it's based on the Newton and Euler, right? It's kind of the first step for when you import some object into the physics engine, it will calculate center of the mass, and afterwards it will pretend that the object is kind of just one point. The usual forces working on it, and basically you can even usual math, school level math for the state evolves with the time step, with the discrete time step. So it's like a pretty simple solver. There are a little bit more complicated solvers, but in general, that's how it looks like. As well, if you look at it, it looks like a state, a little bit like a state. If you squint, it looks like a state space model. And that's actually where the state space models, they come from physics. So they're kind of this.
And what is R?
R rotational matrix, basically, for the translation and the rotation. And it's at this point when the simulation is happening, it's kind of we simulate as a point in space. It's called transformation matrix. We have a position, we have a rotation, we have a scale on it. And we are going to map the geometry on top of that. So okay, our object moved. We have 2 spheres, very simple kind of problem, right? We had 2 spheres, they moved and they accidentally overlap. What do we do? We need to solve. So one solution, of course, we take those pairs of the object, right? And we kind of do something to solve. In reality, we will have not 2 objects, but like thousands of objects. So a very important part of the physical engine is the spatial hierarchy. So which we will reduce. Basically, the spatial hierarchy will allow us to not try to, fix every pair of the objects in the scene, but only the pairs of the scene that are important. So, for instance, if we have like a bunch of objects in space, we most likely will construct a special data representation that will group those objects that are close together, right? And we will create this tree. And then when we want to figure out, okay, are these objects are overlapping or not? Do we need to serve them? We're going to check on this some pairs, and we're going to traverse this tree. So it kind of reduces the complexity of the problem from n squared to n log n, or maybe n, depending on the situation. And there are a variety of spatial hierarchies that people figured out. And some of them are better for static objects, some of them are better for moving objects. It depends on the shape. It's definitely not all the spatial hierarchies. This is like a million of them.
But as a user, you never touch these, right?
Yeah, you don't see that.
You don't see them even.
Yeah, but I want to tell you what is happening under the hood, right? So
for the objects that are crossing the boundaries, the cells, are they contained in both?
in both. In cases like this, they will be contained in both. Or maybe they will be contained, not necessarily in both, but they will be contained in a higher level. Not in the leaf, but in the middle. There's so many implementation.
Is it approximative? Like, do you ignore some collision or?
At this point, yeah, it doesn't. At this point, when you create a spatial hierarchy, it does not know anything about the collision. It doesn't care about the collision. It just looks at the objects that they are close together. We'll put them together in the same day. This is just to reduce the complexity of the operations. Because imagine you have 1,000 balls in your environment, right? 1,000 spheres. And all those spheres potentially can interact with each other. So if you have to check them, if are they interacting or not, are they colliding or not, you have to do like 1,000, take one sphere, right, and compare it with 1,000 other ones. Take another one and do that thousand by thousand times. But that would be the complexity. You will do a million operations. So instead of doing that, you put spheres or any object into the spatial hierarchy. And now inside of that spatial hierarchy, pick one, whatever you like, right? Which one? So for instance, let's pick this one. And in this spatial hierarchy, it is updated every frame, but because objects can move. But inside of this, you can see that this sphere, I don't need, like inside of this box, there is only one sphere. So I don't need to compare it with anything. I don't need to check it with any other spheres.
What happens if it enters in collision with a small one?
So here, these three are potentially colliding because they're close by. This cannot collide, right? We know they're in a different box.
Okay, so it's assumption that they are at different places, so they will not collide.
Yeah, you just look at them, right? It's not an assumption. You actually look at you update the spatial hierarchy by looking where the objects are.
Yeah.
And you create this simplified space representation, right? You take your space, you divide it in half. You see, okay, spheres to the left of this line go into this node.
So
Spheres to the left go to that.
and when the object moves,
It will
you
change.
do, okay.
It will change, yeah.
Do you only stay within a box, or do you also consider interfacing two boxes? For instance, one of the small ones on the left will still be close to.
Yes.
to another one,
Yeah.
right?
Yeah, it's a lot of implementation and details how people will do.
So how do you go around like doing like creating those areas for those objects? Like how do you create that space?
You like divide your space, your infinite space, you divide it first in half like that. All objects that are to the right go into this part of the node, right? Like imagine we have this, and we're constructing it. Yeah, we're going to split it, and we're going to put those objects that are left from the line that can appear hierarchically, iteratively.
So we're like randomly segmenting the object.
No, it doesn't. It's a standard. It's not really important for the physical simulation. I just wanted to say how it kind of the spatial representation is there, and that's what you need to know. That's it. So okay, two spheres. How we solve that? We need to push them against each other, right? That's kind of logical. We're going to create this impulses here, and those two impulses are going to push the spheres away from each other. Kind of logical, right? The amount of the intersection will tell us how much force we need to apply so that they will separate. And that force is an impulse. It's not a force, it's not a constant force, it's a force that is applied for one t. But what happens if we have three spheres? So here you can see that we have a problem, right? We are pushing this sphere, but it's going to immediately overlap with another one. So how can we solve that? So classical solution is just doing that iteratively. Do that every time frame. You don't solve the one collision or once. You probably solve it like 1,000 times. Okay, let me know how. Depends on the complexity. But quite a lot of iterations have to be inside the main iteration to solve all the contents in a solution. So, although it's kind of very simple topic in terms of there's no research. We all know about the physics. It's like a completely scientifically solved problem. Engineering-wise, turns out to be quite hard. People spend years on that. Like there's just one book here that specifically works on collision. There's another funny book here. It's just about visualization of quaternions. In physical simulation, you use quaternions quite a lot for communication. Okay, so. And then on top of that, we have to add even more like drag, springs, and all that. So here you can start seeing the real problems, right? When we have chained objects, when we have a lot of objects on top of them, we have these things, and then we move in freely. You can see how many collisions. Like if you have a belt running around the wheel, right? You have like a ton of collisions. That's why people have to use it. And the problem as well is like all this system becomes very unstable. Like you move it a little bit, right? You solve the collision here. If we move a little bit, everything is going to propagate. And all those guys start to jiggle. So that's the actual engineering problem. Yeah, so in general, going back, how it's on a high level, how it works, basically all those collision detections are going to be converted into these constraints, all these joints, springs, everything is going to be converted to the so-called constraints. Like certain things have to stay together, or certain things have to move a little bit. Those constraints are going to change, to be transformed into impulses, and the impulses are going to be applied to the object. And then we have this solver that creatively applies to the thousands of objects, trying to avoid this jittery, kind of problem.
What do you mean by constraint? Because I was thinking you get forces for the collision and then you add them to Newton. Equations.
Yes. So we can call those we call all of that constraints. So basically,
Forces that you add in Newton's equation.
Basically you can think that first you create a constraint, and then from that constraint you figure out what is the input. And the constraint can be not just collision; it can be like a joints, for instance, right? Which are somewhat connected things, or springs. So from all that, you create constraints, and from those constraints, you solve them, you figure out what the impulse is. And it's kind of, you can think about all of that is just forces, yes. In the end, it's all just forces. It's just, on the engineering level, it's a little bit more complicated because you have to avoid certain instabilities in the system. And there will be a lot of instabilities, like you can see here, like a lot of, when the objects are touching each other, they're resting on each other. There's constantly some form of a kind of forces working. That's why, as well, that's why I say constraints, because when the object is on top of something, right, it's the gravity works it down, and you kind of have to push it all the time up. But if you do that, you will get this kind of jitter effect. What you want to do, you want them to be lying on top of it, resting context, right? And that's why it's kind of constrained, because it's a little bit harder than just creating positive force. And again, we apply the same logic here as with the hierarchical representation for the collisions. When you solve those impulses, because they're going to propagate, there are some ways to split your scenes into hierarchical representation in order to just reduce the computational costs.
So at the physics level, basically, we make the hierarchy. And that exists already in the engine.
Yeah, all engines there. That's the basis part, kind of the basic part, basic components. That's what kind of is I see in all engines. They will have spatial hierarchical representation. They will have this body dynamics, and they will have rigid solvers. That's kind of
the hierarchy is purely spatial.
Yes, it's purely spatial.
Purely, I thought you wanted a hierarchy that's physics based.
No, they are purely spatial. I mean, at least as far as I know, they are always purely spatial. So I'll throw more problems at you, right? So, okay, geometry, how do we represent, now we know how to move the objects, right? How do we represent their shape? They are not just points in space, they actually have shapes, right? So, okay, if we can use primitives like spheres, cubes, capsules, bless you. Capsules are very popular in physical engines. So if we do them, they are quite simple because it's just a function, right? It's a function, you can represent them as a function, and you can do all of that. That's a very simple shape. If we want a more complicated shape, like a teapot, we have to, it's a geometry. And geometry, it's in computer graphics, it's called a mesh. It's usually made something of the polygons, right? It's an approximation of a shape, 3D approximation of a shape. This is quite famous, actually, object. It's one of the first ever scanned teapot in computer graphics, Utah teapot. But anyway, so you can see that we create the surface of it. The problem is we create the surface of it, right? So it's thin, it's hollow inside. There's nothing inside. There's just the shape. Although our physical object has something like usually material, right? In computer graphics, when we scan them, we get only surface. And here the problem with collision, right? You can probably see the problem. Okay, if the ball is outside, fine. If the ball is intersecting with the teapot, or you can with the surface of the teapot, we can detect that. But if the sphere is inside of the teapot, we have a problem. In reality, it cannot be there, right? There is a material there. In computer graphics and physical simulation, it's just hollow inside. So it's quite a big problem.
this may be a, hope it's not financial, but can the teapot break?
Let's not even go there. It can, but that's
Depends on the game.
on a physical simulation. Yeah, I mean, for robotics, you probably don't need that much. Maybe but for cars, for deformations, like so these are a whole topic of deformations. They can be like a surface deformations. They can be material like lots of elements deformations. We actually did a small deformation engine on the way on the airplane here for the robot. So, but basically, if you just do a lot of particles and then you try to simulate, and then if you break the object, you will create a lot of kind of parts. They can be particles lying on the inside of the object. A lot of complicated simulations there. So, for instance, if you have some geometry, what we can simplify it in a couple of ways. We can either take a bunch of those primitives, like spheres and blocks, and we can just approximate it. That's one. Or we can create a very simplified geometry, and maybe we'll have less problems with that. But usually it's just a combination of some kind of simple shapes that can approximate physical. So quite often when you do the physical simulation, it's not really real. It's some form of approximation because the mesh itself, because it is hollow, you can't really use it. For precise physics, it's impossible to do. So you have to approximate it with some shapes, and then you can see maybe here thin lines. This is the approximation of that complex object. You can see that there is quite a lot of difference between the real kind of stand object and what we are going to use for the simulation. So that's a huge source of imperfection. One way to solve that is this. I don't know if you can see that this sign distance field. So when you scan the object, afterwards you do something. You try to figure out if are you inside the object or outside, and you create this volumetric matrix or tensor of data that tells you how far you are from the surface. Are you inside? Then you'll be negative. If you're outside, you're positive. But it tells you the distance to the closest surface, and that helps a lot with both collisions. And for the solving, it makes the physical simulation much more stable. The kind of very interesting thing that happened for the neural representations of this SDF, we can actually take, because it's just a kind of three-dimensional tensor of data, what we can represent it as a function of position. So basically, it's a function from the position you go to the value, to the distance, to the surface. And you can train a simple, like multi-level perceptron feed-forward networks that approximate that function. And that's what was done with SDFs.
Do people use that now in these engines? Not really, right?
Not really, yes. But that makes it differentiable. Like if you have that, you can solve a lot of problems that make a lot of. It enables differentiability on the contact maybe level, on the collision level, because otherwise collisions are, like he has pointed out, are not differentiable. And one more problem, just for fun, is fast-moving object. Because we're working on the time steps, if the object flies fast, right, you can see the problem here, right? Probably. Just going to skip if you have like some physical object, some cylinder, say, and we have a traveling spheres. This one is going to correctly intersect, and we're going to catch that, and we're going to push it away. This one is going to skip just because it's going so fast, it will jump in one time step, it will jump over the obstacle. So it's kind of quantum physics, but we don't write that. So one kind of simple way to solve that, you can stretch it on. Instead of just having them in time steps, you actually, when they move, you take the sphere and you stretch it in the direction of them. There are other ways how to solve that. And if you start thinking, how would I stretch a rotating object? Good luck.
So why do I still clip through all my games then?
Yep.
But I'm moving fast enough.
Yes.
Why do all the game engines still fail?
Well, because it's a trade-off, right? But for the physics simulations, you would do that, something like
In
that.
VT engine, you can choose 3 collision modes and you will choose different mode bullets.
Yeah, it depends, right? It's like performance versus your quality of simulation. It's a trade-off. Yeah, the future is differentiable for the physics simulation. There are already existing physical simulations that do differentiability. And the problems like dynamics, geometric, like simple primitive dynamics, they are differentiable out of the box, no problem. The meshes and the collisions are the main problem. They are not differentiable kind of by definition, and it's not clear how to solve it. Joints are, I'm not sure they are kind of, some of joints can be differentiable, and some have like breaking conditions that are really hard to differentiate. And this SDF side distant field, though, especially with the neural representations, they kind of help to close the gap in terms of geometrical representation and collision for the differentiability of the edge and the physical edge. And why do we want the differentiability of the physical edge? First, it's of course for reinforcement learning. Because when you have kind of in physical simulation inside your reinforcement learning, you would want to know, you would want to propagate gradient through the whole kind of back-to-back from the simulation down to your neural network. Instead, if the physics are not differentiable, if it's a classical physical engine, then you will have to sample a lot in order to feed into your reinforcement learning. How much? Okay, so do you have questions about the physics? Have I bored you enough?
Go ahead.
You're only doing simple geometries, not like self-taught or.
I mean, you can do that. I just didn't put that in the slides because that would be 2 more hours. But yeah, breaking soft robot, so it's quite complex, right? Most likely you will go into the particles. You will go into solve them with the finite elements. You just have it. Can't use that word. A lot of particles that would approximate your objects, and then you can tear them, you can deform them.
Well, it's just when I've seen most neural networks now taking over, rather than trying to do the particle physics, you just run a neural network and then just hope you got to.
Hope is the key word there. Yeah.
Yeah, I'm just curious, and if the answer's too long, don't worry, I'll take it fine. But it seemed like the state equations were just basically turning physics, but obviously there's been these other abstractions like Hamiltonians and everything been developing. Are they how the physics engine actually works, or is it really just back to the first principles?
It's back to the first principles. I don't know if there are people explored other possibilities, but I think there's just in the end there's so many kind of issues that are hard to solve, or they introduce instabilities, numerical instabilities, for instance. So people just do, reducing your time step is quite often the easiest problem, the way to solve the physics. You just try to do it faster and in more steps, and that's it. It's better than doing it with less steps but smarter. That's what people kind of figure out so far. Because as well, our computation is rather infinite, as we know, right? Our computational power is infinite. Especially if you use good machine. Okay, so sensor simulation. So next step is of course we have to render sensors, and usually again I think people think more about the robotics in terms of the physical simulation, but of course sensors are a very big part of the simulation. And yeah, so there are various sensors that we have to simulate, and if we take like a classical, let's see, game engine or some form of a simulation, like a classical simulation engine that is used for movies or games, doesn't really matter. You can easily generate nice looking pictures with it, right? And that is pretty much that simulates your camera. That's easy. But what else can we extract from that? We can of course extract the object identification. That's quite hard categories from directly from the engine, and that helps a lot for if you want to segment, for instance, do the segmentation of the image segmentation. So for instance, if you're training the vision and you need a lot of segmented images, one of the kind of easy way to do that is by using rendering engines. I mean, it's easy to extract depth and optical form. So for the depth cameras as well, it's quite easy to get all that data. That data is present inside of any game or rendering engine. So LiDAR is quite easy as well. Basically, what is LiDAR is rotating thing, right? With the trying to shoot rays, and we can simulate that exactly how it works inside of our graphics engine. And basically by rotating like that and shooting a lot of rays, we're going to find the intersections with the geometry. This is the usual physics simulation engine has this primitives of where you can shoot the rays against the geometry, and it will give you the closest point to you. That's built in almost. So that's for LiDARs, it's really easy to simulate them in such environment, and you get something like this. However, probably unsolved problems so far is event-based cameras.
No, that's much easier than the LiDAR, because the LiDAR has to model also the reflectance of the world, the fact that, for example, the car is tilting up, leaning and rolling and panning. All that stuff. Yeah.
But the problem,
It works pretty well now.
But the problem is that it's not. Yeah, of course. I guess the question is how much of the noise you can tolerate.
Noise smell pretty well.
The noise, I mean, in terms of, because any of those simulation engines, they are going to work in time steps.
Yeah.
And this is not, I mean, if your time step is, if you are satisfied with the time step in terms of the event discretization, then you are fine. But if you want events to be in between those simulations,
yeah, that's why we upsample using super slow-mo, for instance.
Yeah.
You know, so if there's not too much aliasing between the frames, you can upsample very well with these deep learning optical flow algorithms.
Yeah. So it's kind of, but it's not real, right? It's not coming from simulation. It's something that you tweak to trick it to outside afterwards to generate those events.
Anyway, it's very compute heavy, whatever you do there.
I guess the point is that those event-driven sensors are also very noisy, and there's fixed pattern noise, there's.
Yeah, all that stuff is in the models to some extent, you know. You just have to decide if it's good enough for machine learning. Right, motion blur and dot noise and all the non-linearities having to do with intensity are all kind of modeled, at least to the extent that we understand them.
Perhaps what I wanted to say is that out of the box, you are not getting. You need something else, like this upsampling algorithms outside.
Or you try to put parameters that are realistic, you know, how the lots.
So I want to show one real use case. When I worked at Unity, it was like 5 years ago. We had this interesting project of simulating worked with the Bellevue County, simulating a particular intersection. So basically, they have a real intersection. There's a camera that's a couple of cameras sitting there, and the problem they have, that particular intersection has a lot of accidents, and they wanted to solve it. So basically, they went and so the two problems they wanted to solve, it was like they wanted to detect accidents, and they wanted to detect them before they happen, and they wanted to do a lot of kind of vision. And back in the day, the vision was not really solved problem. It's like 5 years ago, and they were doing a lot of manual segmentation to train their vision model. So they wanted to generate the segmentation kind of maps for themselves. So how do you create something like that? It's a pretty complex problem because you have to scan the reality, you have to recreate the whole reality inside of the simulation engine. So you have to, what we call assets, right? We have to figure out the trees, we have to figure out the cars. You most likely have to scan some of the objects, like put them in a 3D scanner, figure it out. For the large environment, there's probably flying with a drone, and once the drone flies around, it scans the environment, then you can reconstruct the geometry. So you can get it pretty close, actually. The cars, of course, you have to just have a library of your cars, and for the peasants, I'm sorry, for the pedestrians, you have to. It's from the strategy game. Sorry. So for the. You basically create a small library of smart components that know how to behave. They pretend to be pedestrians, they pretend to be cars. And then you put everything together, you add parameters, right? The weather, time of the day, all that. So someone has to create, on top of this simulation, somehow has to scan all that has to put it together and has to create this logic of how these things can work together. Once you have that, yeah, you can create a scenarios, how the particularly like how cars behave in reality. Yeah, you can see that it's actually 3D scan now, right? So it's a 3D geometry there. It's not a picture anymore, not a input image. And you can see that we can extract a lot of different information. We can make it look like the camera, and we can extract word like segmentation maps, so that they can train the vision on top of that. Yeah. You can see.
That's simulation, right?
Yeah, that's simulation basically. That's simulation. You can see that segmentation. You can do the sunny, cloudy. You can do different kind of variations to your weather. You can add some like a noise part of, and then you can deflect those accidents. And basically, they were training vision. They were using all that simulation. They were using it just to train a vision that will detect a near accident situation. And it looks, at least on this screen, quite good. If you look at a bit closer, you can see that it's not reality. It's quite far from, in terms of the visual quality, it's far, right? But for this overhead view, it was quite good. So yeah, it was a collaboration with Belview. It was installed in a real actual intersection, and they solved some problem. Before I go to the reinforcement learning, there was another project that we did at Unity with OpenAI. Is this, like, maybe you've seen those paper where there's a robot hand that is solving the Rubik's cube. So the most of the work was done by OpenAI, but we just provided kind of a simulation environment. But the one thing that we learned by doing it, that you don't really need to, like for the sensors, turns out you don't need to make them as realistic as possible. What works better is to create variety. It can be wrong, but as long as you have a variety, it's actually like a lot of wrongs makes one good in there. So, and specifically, I'm talking about the situation that it was camera that was observing that hand.
It doesn't use any tactile feedback, right?
No, it was not. Yeah, it was using only vision.
The shadow hand.
Yeah, and the vision had to kind of understand where the fingers are and how. And it was really hard to get like last 5% of the visual quality. You can see that it does not look like the camera sees the image. Whatever we will do, it still does not look the same. So when you train it, you have some drift from reality. And it turns out that we start basically doing a very unrealistic lighting, just a lot of different, like very unrealistic lighting setups, and that improved the vision quite a lot in there. So basically, we created a lot of noisy samples, a lot of noisy, unrealistic visual sensor samples. But once we get a lot of them, it kind of fixes itself somehow. The probability distribution emerges from that. Quite correct. That maps quite well onto the real sense. So variety was the solution for that.
So
Sorry, I have a question online.
Yes.
Can you hear me well?
Yes.
Sorry, once you have these sort of simulations, what is the method that you can use to like evaluate the accuracy between like the real scenario and the simulation you just created? Like how do you assess one simulation is better than other?
I mean, the problem with this talk, I'm talking about the problems. I'm not giving any solutions, right? So there is no, I don't know if any way to do that right now. I'm sure people working on that. I don't know any of that. It's an open problem. It's a very good question. It's a completely open problem.
Okay, thank you.
That's a related question. So once you write your game engine, you have a huge amount of parameters. How do you fit them to the real world? Is it like for every object you fit parameters and then you put everything together and you hope it works? Or you have like at the end a holistic optimization of all the parameters?
No, there's, at least in this case, you could use that, right? But in this case, there was quite a lot of manual labor work. And but as well, you can think that a lot of you can get like by scanning, just flying with the drones, right? With the cameras, you get it's like a SLAM type of SLAM problem where you get the geometry back. So a lot of that geometry you actually get. And then you could probably use some form of like fitting objects into that. But in this particular case, it could not use. So it was a bit of a manual work to do that. There's a bunch of people that know how to do that. So it's just manual work. A lot of like that was actually one of the problems when the company started doing the autonomous driving. They were coming to us and saying, well, give us this world thing, like, and they're saying, do you know how much it would cost? So somehow people imagine that there's an easy way to scan the reality and get it into but it's a very good point that you actually, it's a lot of manual work where you want to fit the parameters. Our answer was like, do you know how much GTA 5 or GTA 4 cost? And you will have to pay much more than that. And GTA is one of the most expensive games. GTA is the Grand Theft Auto where you drive in the city environment.
10 minutes.
So I think I can just go more to the questions. I mean, reinforcement learning, or cool, like you need all that to do the reinforcement learning. Differentiable physics is really good for the reinforcement learning. Once we have that in the physical engines, more at least more.
People that really need to know this stuff. So what are we doing here? This is largely going to be a tutorial. We're going to go through the 101 of LLMs. Then we're going to go through a slew of techniques that have been adopted to make transformers efficient. I think most critically, most of the techniques that I'm going to spend time on are not necessarily research-based anymore. They are deployed, they are useful, they are functional. They're in open source models that people use. They are in closed source models that people use as well. We'll then go into the more exploratory stuff, things that have been talked about quite thoroughly within the LMP group, within the NIT group. And we'll go into the more researchy things over here when we talk about language models on neuromorphic hardware and the future of LLMs with the whole reasoning saga. But before I go into AI and fancy stuff, I want to take a step back, precisely 30 years back. Very, very cute picture of me when I was a little more cute than I am now, holding my sister's. Thank you, Paul. We've got a. What was that?
You cost yourself.
This is all very self-inflicted, but no. So I was 3 years old, so this was just under 3 decades ago. And my sister, she was 5. My sister was given this robot for Christmas, the XL2, very fancy AI model. We can zoom in, we can see that it's powered by very futuristic cassette-based technology. But yeah, my sister was very irresponsible, right? She gave it to me. I was psyched. I was very, very excited. I don't know if you want to give robotic power to a 3-year-old, but I ran away. I was like, fuck yeah, this is sick. And she calls out after me and she's like, it doesn't cost you to say thank you, Jason. But then this was a slow burn. I waited 3 decades, but I'm pleased to announce that it indeed does cost you to say thank you. Precisely, apparently, like, I don't know, millions of dollars. So, I don't know, suck it, Tash, like whatever. But with that being said, let's see what ChatGPT knows about the cost of running these models. I can ask it how much energy did it cost to train you. And it's going to do what professors are really good at and sidestep the question while talking about everything else that I don't care about. But it does have a bit of a sense of information I do need to know. It tells me that hardware plays into it, the amount of tokens that I train my models plays into it, the size of the model plays into it. All this stuff, it's relevant. The real honest to goodness answer as to why it doesn't tell me is because ChatGPT is closed source. It's not something that's gonna divulge. So let's modify the question a little bit. And this time, actually, no, I'm not going to do that. Rather, I'm going to hit you with a pop quiz, right? What's the energy bill of LLMs in dollars? Training, inference, let's assume the GPT family. Ideas, order of magnitude.
How much you got?
Fuck it, I'm not going to wait for a serious answer. So inference on the order of 1 million per day. It's serving many users, hundreds of billions of requests. Training, that's a one-time cost, $100 million. Now, historically, I think that people were concerned about the cost of training, but now that LLMs have effectively been commoditized, inference is just that much more of a bigger deal. What do you want, Mike?
For these models, how many days do they actually like kind of useful? Like I feel like a new model comes out like every half a year or something.
Yeah.
So like what actually is like the number of days that the model is seeing this kind of workload?
That's a really important question, and it's something that you can Google. So I don't know, man. 12 months. So that's my vibe, right? Is 12 months a fair thing to
Also
say?
distillation and stuff like they still use
They
the
can
minds.
reuse. Yeah.
So the real answer is that OpenAI is going to do everything in their power to continue forcing everything into one super intelligence model, because then they can continue to improve it over time and then serve out, whole other versions of it that are distilled from future versions of it. But like the answer depends on which company you work for, is the real answer.
Yep. I'm not going to add to that answer. Thank you, Guido. So with that being said, let's just go through the low-level LLM 101 tutorial, and we're going to go pretty deep. But yeah, back in 2017, a team from Google Brain uploaded this inconspicuous paper. I think it's painfully uninformative title. But really, the purpose of calling attention is all you need is really because they didn't propose or invent attention, right? It existed. You had cross attention for translation, etc. But classically, sequence models were used for sequence-based data, right? And attention was always hybridized with sequence models. So what this paper really showed was that you don't need the sequential stuff. You don't need RNNs, you don't need LSTMs. You can run with attention alone, right? And the architecture looks something like this. And I don't know, you can kind of see two pathways here. You've got some encoding, you've got some decoding. I'm not going to go into that because ultimately nowadays, all prominent language models kind of just rely on one of these here. Let's see if I can get rid of this.
Computer.
Oh, the computer. Yeah, thanks, man. Yep, so most canonical LLMs that are deployed nowadays just use this decoder-esque architecture. And I'm going to use GPT-3 as your kind of representative model to express what the parameters of everything are. Just note that all LLMs nowadays tend to follow a very similar structure. So what is the anatomy of a language model? So let's take a sentence, the cat in the, and we're not passing in words to a model, rather we're passing in embeddings of bite-sized pieces of words, but let's just assume for now, for simplicity's sake, that we've just got a single vector for every single word, the cat in the, and in GPT-3, each of these words is represented by an approximately 12K vector. They are passed into 3 linear projections, that is a QKB matrix. Each of those generates a 128-dimensional embedding vector per token, right? So 3 vectors for every single token, or if we go with words, you're going to have 4 of them. Then we take this Hadamard product, or this element-wise kind of product between every single one of these kind of Q and K vectors, right? So this is this dot product, sorry, not a Hadamard, but rather a dot product, and you're going to sweep across all the query vectors on the x-axis. You're going to sweep across all of the key vectors on the y-axis. And I don't know, I suppose intuitively, they just represent these tokens in a different form, right? Interpretability isn't too much of a thing here. But Q1 to Q4 encodes the tokens, the cat in the. K1 to Q4 does a different encoding of the same sentence. And by taking the dot product of every embedding with every other embedding, this effectively tells us how related is each word or token with every other word or token. And the answer is just going to be a scalar value. And I've swapped out clunky vectors with circles that represent how large the number might be. So yeah, take note of this large value, right? This relates the query cat with the key in. So the model kind of understands that the cat must be situated in something. So in machine learning lingo, we say that the key in attends to the query cat, right? And we normalize everything by dividing it by the square root of the embedding dimension d, which helps with numerical stability. I'm just going to kind of obfuscate that out of the way because it's not a big deal. It is in practice, but don't worry about it for the explanation's sake. And then you apply a softmax operator to everything column-wise. So as a refresher, the softmax turns a list of numbers into a probability distribution. In this case, you're going to see large values amplified while small values along the column are squeezed smaller, approaching 0. And so this is done for every single column, ensuring that every column adds up to that 1, because it's a probability. Let's go back and replace these with numbers now. Indeed, every single column adds to 1. And so when training a model, you want to take advantage of a couple of things. You want to take advantage of the abundance of data. You want to take advantage of the parallelism of GPU. So when you have a sentence such as the cat in the hat, I don't know, sat on the mat, there are effectively 8 next token predictions here, just by kind of masking every word and exposing it. But then, so there's 8 next token predictions you can generate from like a single sentence. That's nice. But then there is a risk here, and that risk is in this matrix, right? In this matrix, Q is asking which one of you tokens is tightly related to me. And so we need to zero out all future tokens with respect to past tokens, right? And so that means that this lower half diagonal is going to need to be zeroed out. Doing that at this stage would mean that the columns no longer add up to 1. So we apply what's known as a causal mask, where before your softmax, you apply a negative infinity to all of those kind of non-causal elements. And once you scale all of those elements by that negative infinity, you apply a softmax, then that's going to null out all of those values to avoid any future time leakage or future token leakage into the past, right? Awesome. So with that being said, you run through, the goal here is to get the next token. You have a set of options here. I'm not sure which one of these options is going to kind of manifest itself, but ultimately we're trying to find the most probable option and take all of these tokens, the cat in the, and we want to somehow enable this model to understand that there's information at every one of these steps. We need to combine all of this context from that sentence, and we need to combine it with this attention matrix. We want to take the values from this attention matrix and find a value that could potentially be added to all of these vectors here in order to change what those vectors mean. And in doing that, you're able to kind of combine the information from your input text, combine that with the relationships between all of these keys and queries, and use that to modulate some value that leads you to getting your next word, right? There's a lot of steps just to get one single word. So we finally use this value vector, we scale it by all of these scalar values. And I guess the intuition here is that if there's no relationship or a very weak relationship between Q3 and K1, which I guess is the and in, there's not much information between those two words, then we're going to take this value vector and just get rid of it. It has no influence on the text in the course of trying to predict the next token. So then you end up with this scaled list of value vectors. We're going to sum them up, and that gives us this suggestion of a change, delta E, right? It's an embedding vector that is suggesting how should we change these vectors. And you do that for every single column. Again, you sum them all up, and so now we have 4 suggested changes. Right? We have 4 input tokens and 4 suggested changes. All of this, though, is in a 128 embedding space. Our initial input tokens are in that much higher dimensional space. The dumbest possible thing you could do is just down project it into a smaller space. And so you, up project it into a higher space. Thank you. And we end up with suggestions for changes to each of these tokens for every single token. We add these delta E's, delta E dash, to all of these input tokens. And so now we're kind of seeing, okay, this is how information is combined from, cat in the into the first the. All of the words have somehow amalgamated information and made some suggested change into what the representation of that word might mean, right? A single word might mean many things, right? Queen, for example. Queen could be Queen Elizabeth, or it could be Queen the band, right? So by having a sentence that gives you that context, you're able to kind of make a suggestion to kind of refine what that meaning of queen might actually relate to. So congrats, you've mastered attention. Really what happens in practice isn't all of these operations in silo, they're combined into this QK transpose format. And in an actual implementation, this WQ, WK, WV, that all these matrices are concatenated. So they're all taking place in one swell hit. Few things are missing here, such as positional embeddings, multi-head attention. In the case of multi-head attention, what really happens is all of those operations that I just spelled out for you are going to be duplicated in parallel n times. In the case of GPT-3, there are 96 attention heads, therefore this takes place 96 times in parallel. That means you have 96 of these QKD matrices, you have 96 of these delta E embedding suggestion changes. And how do you combine 96 of these? Two options: concatenate them up and then up project that into whatever space you want, or sum them up, right? Both seem to work. All right, that's not it though, right? We still have to come out with an output answer. So we're going to take these 12K summed vectors, you pass them through an upward projection, 49K embedding space, you apply nonlinearity, do another dimensional change, you apply a residual connection, and then you do another normalization, and then you repeat that 96 times in order to get the next predicted token, right? You're going to have a logit value for every single item in your vocabulary. Yes?
The 96 heads, how do they differ from each other?
How do they differ from each other? Okay, well, the process taken to calculate them is identical, but ultimately what happens is that every single one of these weights, or everything in your QKD matrices, are going to be initialized randomly, and so it is thought that every single head may contribute to some alternative meaning of your input token and latent tokens. Less heads, less performance. And we've seen that in compressed KV cache approaches. So yeah, Claire.
Is that proportional then to the number of words that you have in a language? Say.
Not necessarily in the heads. Typically what you would observe is that the thing that is proportional to the number of words in a language is the vocabulary size. So for example, if I have a model that needs to be able to speak to me in Chinese, I'm going to use a vocabulary size of 100,000 tokens. If I do not need it to speak to me in Chinese, I can condense the shit out of it and get away with something like 25K vocabulary items instead. Number of heads, that's...
Isn't it related to the fact that a same word can mean different things, though?
Exactly. So
the more vocabulary you have, the less that is likely to happen, isn't it?
I don't want to give a solid answer to that because I'm not sure, right? I feel as though if you have the same number of heads for differently sized vocabulary, then it just means you're able to get a richer representation for each of those original items in your vocab. But I say that with a lot of uncertainty. Yeah.
So one thing here is that it's really easy to explain this in the sense of disambiguation, right? But it's not exclusively doing sense disambiguation. Every token is attending to every token that has happened before it. So if you have a language model with 128,000 context window, that word looks at the last 128,000 words and decides what it needs to, how it should transform itself in the context of everything. So that's more than just kind of disambiguating between queen and queen. It's also kind of like, is the queen going somewhere? Well, maybe now we start to mix in some information about the place that she's going, what her motivation might be for getting there, and like what.
And these types of things start to manifest in deeper layers, much like in our convolutional neural nets. Early layers are all about just those edges, right? But then you chain a bunch of edges together, and V5, V6 starts to it enables learning context, something a bit richer. Language, we feel like that is much the same, right? So it's not just disambiguating queen and queen. It is, the queen lives over here and is doing this, and you will have a vector that hopefully captures all of that information. Those multiple heads will kind of work together with each other to get something a little richer.
The other standard thing that we need to announce in a room full of neuromorphs is that you might notice that this sense of the word attention is completely different from the sense of the word attention that shows up in your brain. And most of the rest of his talk is going to likely be about hacks to this type of attention to make it less painful to compute, because it's just like this all pairs stacked, dozens of times. And so it's a horrendous computation. Attention in this scenario doesn't save you any computation at all. It's still
expensive.
Those map moles at every single place all the way through the network. Whereas in your brain, attention is used to like pare down the computational paths and directions that save you computation.
Yeah.
So just kind of wanted to make sure that Ernst isn't sitting over there kind of stewing on the.
No, but I think, I mean, what this kind of attention is, it's much more in visual people call it, or sensational, perceptual organization.
Right.
I mean, make having entities in your input that make sense, and then treat them as entities, not as individual features. So that's completely different from selective attention.
So in the interest of turning a 5-hour talk into the next 45 minutes, I'll keep going. The output of all of those 96 steps ends up with a probability distribution that adds to 1. How do you choose the next word based on a probability distribution? Okay, you've got greedy decoding, you just pick out the largest value, or you could sample that probability distribution where it's going to be sampled with a 99% probability, hostage negotiation with a 1% probability, right? Very abstract toy example. Cool. Then you take that word, dump it back into your input, make space for that new single input, and go through this cycle again and again for every single word until you reach an end of text or end of sentence, whatever token, right? So you're going to introduce a new vector. That new vector, Claire?
And it's typically sampling from the distribution, not picking the highest, so that each time you input a sentence, is going to
Bit of randomness. Yeah. So one thing that I haven't brought up is the concept of temperature. If you were to increase your temperature, you're changing how the softmax is applied, and higher temperature makes for a more uniform distribution. If you want to get a bit more creativity in your output text, ChatGPT or OpenAI limit the temperature component, the index of your softmax to 2, I believe. And I guess that's because they don't want to have super weird outputs being generated. Weirdness to a point, but to the point where it's called creativity rather than just being straight up wrong.
Also prevent people from reverse engineer, right?
And also prevent people from reverse engineering. Yeah, I guess that could help. It could also lead to. No, okay. So we're going to take that token. We're going to take that one new token, and in the process of what I'm about to show you next, keep this in mind, right? Everything I just showed you before, rely on the fact that we already had a bunch of inputs. The cat in the. Now, all I've got is one new token to process. Ask yourselves what can be reused from the previous cycle of computation in the next computation, right? So we take that embedding for hat, pass it through the same process, and we need to make space in our attention matrix with this fancy ass animation. We need a new column, we need a new row, and what are we going to do? We need to take the query and value dot products. We need to take the queries and values for every single previous token. What does that imply? It implies that we should probably store all of our Q values from before, and we should probably store all of our K, our key values from before. But then we take the value, and of course, we've also got this row. We're implicitly applying that causal mask, and we know that softmax is going to turn all of that to 0. So we just pre-fill it with 0. Don't worry about that bottom row. We're not really doing anything there. Then we need to take all of these value vectors. I've realized that I misspoke. We need to store K and V. We do not need to store all of the query values, right? We just take Q5 from hat. That is scanned across the entire column. But with our keys and values, we need the entire history of our keys and values. We generate a new suggestion for an embedding change, delta E. That gets passed into the upward projection, that changes the hat, then you pass that through your entire forward pass down to the bottom, your feed-forward networks down there. Mike?
I thought when we calculated the vectors before, we used like the blue vector when we calculated a delta E, and we added that to the original vector. So isn't that going to change the K and D vectors?
Say it again, sorry?
So you added the delta E's like, to your vectors, right?
Yes.
So doesn't the K and D vector change?
When you add this to this, that's your output. You're not recursively changing your input. So it's not like you add this to that and then repass that.
So the blue vectors are basically fixed.
The blue vectors are fixed. Yes, good point. Go.
And that basically means there's no way of going back. So let's say later you figure out, well, hat was not quite the best thing to do.
Yeah, exactly. So yeah, not bidirectional. You can't go back in time and say, oh shit, I suggested the wrong token, unless you were to just repeat the process. Now, I'm not going to bring that up here, but there is this emerging, I guess, application of diffusion to, yeah, you got it, diffusion to LLMs. And that does let you denoise everything in parallel and use later tokens to fix earlier tokens. Yeah. Reasoning doesn't do that, but in a similar direction as well. Intuition, everything up top is concerned with how do we update our meanings, our definitions of all of these words. How do we combine context amongst words and tokens? Everything down here is like, yo, I've got a ton of data from the internet. How do I get all of these combinations of context, of tokens, and use that to understand something that is already out there? So everything down here is thought to compress that internet, I guess, richness of data in order for you to come to conclusions based on facts that are outside of what your input sentence might be. So let's highlight this. I want to take a moment to consider this attention matrix. And if we were to start processing super long PDF files in the way that you might upload something into the ChatGPT API, then say if we had a context window of 1 million, as is the case with Gemini, and one of the Llama 4 models, then you're going to end up with a 1 million by 1 million matrix. That is 10 to the 12, 10 tera elements in your matrix. Now, do you want to recalculate 10 to the 12 elements? Absolutely fucking not. So we need to rely on that KV cache, and effectively all we're really doing is recalculating that final column for every new input. So that's the point of storing all of the previous keys and all of the previous values. And the two things that I did to calculate this new column is I took the dot product of K1 through K5, multiplied it by V1 through V5, nothing else in the attention matrix changed. And so that means instead of recomputing 1 tera elements at every forward pass, all you really should do is store your keys and values and only ever operate on those. This is known as the KV cache, and this enables us to avoid recomputing the entire attention matrix by storing prior vectors. This also raises an interesting distinction in the types of workloads that are needed to be optimized by language models. Prefilling and autoregression. Prefilling is also called ingestion by some, and autoregression is also called decoding by some. The idea is that with prefill, it runs a huge number of operations, but all of those operations are highly parallelizable. That the prefill takes place, when you might type in a bunch of text into the chat box, then you hit enter. All of those tokens are now available to your model, but your future tokens are not available. So once I start running hat sat on the mat, those are generated one at a time. So fundamentally, they're two different types of workloads. What this means is that prefill is a typically compute-bound process because there's so many fucking operations going on to generate that entire n-by-n matrix. And when you have a large model at the hundreds of billions of parameter scale, then it makes sense to have your most expensive GPUs allocated to this type of process. So what you will actually see is that prefill, with companies that can afford it and have the manpower to do the engineering related to it, prefill is allocated to expensive fancy A100s, H100s, H200s, while decoding is typically IO bound rather than memory bound because you're only ever calculating one column at a time. So those go to high performance, but not necessarily server class GPU. I shouldn't say server class, but things like A6000s. And so yeah, two different processes, two different GPUs is going to be the cheapest way to achieve all of that. So with all of that being said, yeah, autoregression is IO bound, and that really covers the backbone of all modern language models. You know more or less all of the operations that take place in attention. Of course, there is normalization, positional encodings, and things like that I've ignored. If we go ahead and have a longer chat, then I can give you some more intuition on what all of that does. So let's generalize. This is just one of many transformer architectures. Let me try and distill all of those clunky pieces into something a bit more generic. Token mixing. Token mixing, the idea that we have tokens and they need to kind of be combined somehow in order to update each other's meaning, their context. Channel mixing, all of the feed-forward layers down the bottom, where you're mixing information from your input with an internet-based wealth of data, right? Normalization and residual stream. So these bottom two are really just related to enabling gradient flow in very deep architecture. So these two are really the backbone of computation, and these are just there as supporting acts to make things work, right? And we take all of these together, we pass them into many blocks in an architecture that looks something like this, and this is very generic, I think. Most LLMs will do something very similar. Your tokens go in, you apply your token mixer with a residual stream, you apply your feed-forward layers in the channel mixer to another residual stream, and you repeat that through n blocks, with your embedding on the start and the unembedding at the end. With that being said, let's now consider how to make transformers efficient. I want to do this in a way that starts by asking the question of how do we keep self-attention? So we don't actually modify any of the operations, we just modify the implementation so it's more efficient. I want to look at techniques that supplement and kind of add on to self-attention, and then I want to look at weirder shit, things that just completely replace self-attention. A very reasonable question to ask is, should we even be targeting self-attention? Because there's so many goddamn feed-forward layers in transformers. And so this plot comes from an analysis of how many flops are being utilized on a state-of-the-art QN open source model, where on the x-axis you have an increasing sequence length, and on the y-axis you have flops. Blue denotes the amount of ops allocated to attention, orange denotes the amount of ops allocated to the feed-forward layers. So with smaller sequence length, it makes sense that attention is much cheaper because that attention matrix is much smaller. You have less context to have to process, so that n squared matrix is heavily compressed. So maybe optimizing attention for a task that relies on 100 tokens is probably not worth your while. Maybe then you want to quantize feed-forward layers, right? As you go through larger sequence lengths, that's when targeting attention makes a bit more sense. But having said all of that, I don't know, vector matrix multiplications have been around for a lot longer than self-attention, and so GPUs are already hyper optimized to being able to accelerate those types of workloads, right? For that reason, I'm going to focus most of our time on self-attention. So let's start by figuring out how to keep self-attention. And so what I've listed here are 4 techniques, but really they're actually just rolled into one implementation in practice. This is this is called flash attention, and it combines safe online softmax and block map mole. Let's very quickly fly through all of these techniques. So we'll bring back pieces of the self-attention operation. You recall the first step in the transformer where we take our input embeddings, we pass them into the QKV matrices. We can represent that with this notation here, right? This is just QKT in that dot product operation. That's fine. We've got the column-wise softmax. I'm going to introduce alternative notation for this as well. We'll call it P equals softmax S. And then there's the other bit of attention where we get our output projection. Our output is P times V. So I'm going to chain those 3 operators together, and that is just a really clean way to express self-attention. So what's the deal with all of these? How do we optimize these without changing them? Now, on a GPU, everything is most likely running on a GPU. If I was to, I don't know, when you process things, you have a bunch of cores and they need to access instructions and data from HBM, and that data movement is, of course, the bottleneck to a lot of the processing that we run. So the data bus goes to your global memory, and that data access typically dominates the cost of most things on a single GPU. So if I was to take this QK transpose operation, I need to access a bunch of those values from HBM. Likewise with this output operation. Now, so each of those require at least 1 memory access, provided everything fits on that single GPU. In practice, it doesn't, but you have enough GPUs to handle that. Now, an unoptimized softmax, on the other hand, that can require 2 to 3 rounds of data movement back and forth. Why is that the case? So if I bring up the softmax operator here, there are effectively 2 steps that need to take place. So 1, we need to calculate that denominator. We need to sum up across all our values, we need to raise all of those values to their exponent, and then sum them together. You calculate your denominator. Then you need to run, you store that. Then you need to run through every itemized element and do the division by that accumulation. So that's effectively 2 for loops that you need to run through, right? Bit of a pain. And not just that, but you also run into numerical instability, right? So e to the power of your largest activation is going to very likely blow past what a Brentflow 16 numerical format can represent. Of course, once you divide it down by that accumulation, yeah, sure, that fits within the bounds, but the intermediate steps to get there are going to go past, they're going to saturate what you're able to represent. So you have numerical instability as a result of all of that. So how do we fix that? If we fix that using, I say we, this is the broader community, as if I could come up with shit like this. The safe softmax is where this comes in, right? Like, what's UCSC going to do? Fire me? I dare them. Back to Australia, living the dream. So we're taking the exponential of a list of values, right, of all of our elements. Let's say that we have 3 values in this toy example. So on the bottom axis, for those of you that can see, I've got A, B, C. I raise them to the exponent to get A dash, B dash, C dash. And let's say perhaps that C out on the end of the x-axis has exploded. What can we do about that? Let's say that I take all of these values, A, B, and C, and I subtract the maximum value from them. I subtract C. So we're going to push everything to your left. But we get that this is effectively what softmax is. I need three values, I need three logits, so A dash over the accumulation for A dash, B dash, C dash, right? So let's take the maximum element and subtract C from everything on the x-axis. And so everything is kind of projected onto the left-hand half of the plot. So the maximum exponent is now 1, right? And if I show you A dash, B dash, C dash, A double dash, B double dash, C double dash, and I take the exponent of that, I'm going to ask you, what is the relationship between these two operators? Thanks to the way the exponential works, they are perfectly equivalent. So you avoid numerical overflow just by subtracting that maximum value. But what's the pain with doing that? Can anyone identify that? It's sequential. Bam, you've got a third for loop in that operation. So we go from 2 for loops to having to first find the max, and then we run everything else. You're actually really smart, so I didn't realize that. So 3 for loops. We take that, and so what do we want to do from here? You're going to run into stalls in your pipeline. It's an extra memory access step. What can we do to fix this? The online softmax are effectively going to be fusing operations in a rather intelligent way that, I don't know, to me, from the neuromorphic side, it feels a little bit like real-time recurrent learning and all of those fancy tricks. So let's sub in some actual numbers into those columns, and recall, we're only applying softmax to individual columns here. So I'll just get rid of everything for now, and you can appreciate that things generalize. In this picture, this is what I want, right? I want to step through all of my elements through I, one at a time, and I want to sum them by, I guess, this denominator. I'm subtracting 5 from every single one of those elements because 5 is the maximum value, right? So how can I compress the number of for loops for this? Well, let's say now that we don't have access to the vector and we're going to step through every element one at a time in our first forward pass, in our first for loop, right? I'm going to initialize a pair of states. The first one is our running max value, initialized to negative infinity. The second is going to be something that hopefully ends up being our denominator, right? If I can fuse the calculation of our max value and at the same time with the denominator calculation into one for loop, that's good, right? And then I do a second for loop to iterate through the numerator, and that's the best that we can possibly do. So stepping through all of this, now I've now exposed the number 3. So my max is now 3. And my state, I guess, the potential denominator will be e to the power of 3 so far, right? Let's step through to the next element. Before we step through the next element, we need to subtract the max value, right, which is 3. So we now have e to the 0, which is 1. Cool. Let's go to the second element, 2. Well, the max value hasn't changed, still 3, so we're good. That's fine. We sum our previous value with the next value, e to the 2 minus 3, 2 minus the max value. Excellent. But then this next step is where shit gets a little fucked because we find out that the maximum value is 5, right? That means that everything I calculated in L1 is wrong. How do we address that, right? So, well, we go ahead and we add that e to the power of 5 minus 5 because we now have a new maximum value. Recall that L2 is going to be e raised to the power of these things, but it's used the wrong assumption of the maximum value. It's pretty easy to fix. You just, if we want to convert it to 3 minus 5 and 2 minus 5, as per our golden standard answer, we just multiply it by e to the previous max, subtracted by the current max. And you can see that, you know, this minus 3 and that positive 3 just get rid of each other, and beautiful. We now have 3 minus 5, 2 minus 5, right? So that's all well and good. You do this a bunch of times again and again, which I'm not going to go through, but there is that generalized form in order to update the max value, add in that correction factor, denoted by this term in the red. No, if your maximum value hasn't been updated, that term just disappears, right? Previous max minus current max is just 0, e to 0, 1. Nothing is contributed there. So that's very good. What that means is that, you know, we have compressed 3 for loops into 2 for loops by running softmax in this online fashion, while retaining the safe softmax to avoid numerical instability. But it also feels like everything I'm describing to you is a bit of a fucking joke, because this was just one tiny little thing in all of these other vector matrix mults or matrix mults, right? So in practice, what flash attention does, it takes that fused kind of softmax kernel and it runs block map mul in a way that lets you distribute all of these matrix multipliers at the same time as coming up with that kind of local maximum operator, right? If I was to distribute this matrix multiplications across all of these cores, and for example, you get that, and just spread out all of these little bite-sized pieces of a matrix multiplication across these cores, I hope that you can kind of gain the intuition that even if one of these cores doesn't have access to the global maximum, you're ultimately going to be fine just by using that kind of correction factor at every single one of these cores. So you end up being able to fuse all of these operations into 2 for loops. That's the intuition. That's kind of all I'll go into that. And so flash attention does this. If you're ever calling a transformer from a PyTorch library, from whatever library, what's actually going on under the hood is everything that I've described to you right here with flash attention. So all well and good. What they, I guess, ultimately realized was that by fusing all of these operations, they are able to, on GPT-2 at least, they're able to improve speed by a factor of 10. Excellent. So that is the most common canonical way to speed up how transformers run. Let's now fly through how to supplement self-attention. We can break these down into attention modifications, dense layer optimizations, and perhaps more system level, higher level optimizations as well. This is far from exhaustive, just a snapshot of what I personally find somewhat interesting. KV cache compression is the most obvious thing. That's the thing that kind of scales with an increasing sequence. So if we consider multi-headed attention, where you have 1 KV value for every token, and every one of those tokens has an additional value for every head, with 96 heads, you're blowing up your memory pretty rapidly, right? So let's clean up this picture. Let's compress that one transformer operation into multiple heads. All well and good. Each of these heads have a separate QKV matrix. They have each of those has their own independent KV caches. So the dumbest thing that we might do is use multi-query attention, where you share K and V across all heads. Okay, fine, we can do that. We lose some level of representational capacity. It works, that's fine. Alternatively, we can run grouped query attention, which is what Meta do with Llama. Rather than a single KV shared across all heads, they're going to kind of sub-partition KV between a subgroup of heads, right? Typically with a ratio of 1 KV for every 8 heads. Okay, pretty simple, I think. So keys and queries are grouped between attention heads. Sorry, keys and values are grouped between attention heads. Let's see how they actually perform in practice, right? So with multi-headed attention, with many heads, memory efficiency is pretty shitty because every single head has a KV cache. The performance is good though, because you're using a lot of parameters, a lot of values. On the other end of the spectrum, where everything shares a key and a value, cache, memory efficiency is great because you've compressed everything down to just 1 head worth of KV values, but performance is honestly kind of shitty. You do degrade a lot in performance. In between, grouped query attention, Meta's approach, does both of those things fine, right? It feels like there's this Pareto front and you can't really push beyond that. Well, that's, I guess, where DeepSeek came in. They proposed multi-headed latent attention. I can break this down to you in a little bit more detail if you wish. For now, just, I don't know, trust the janky animations. But what's going on is that they introduce a latent projection before they get to the keys and values. They project the input tokens as such, then they take the key, fuse that with the query, and then they run attention after that, the same shit as before. And then the output projection to generate that delta E embedding, that is fused with your value matrix. So a bunch of things are just combined with a slightly higher dimensionality. And in doing that, it seems that things work really well. What I think the real takeaway is that you can get away with things that are not just 3 linear projections, and it still works really well, right? Depends on what you're doing to some extent, of course. Now, KV is said to be in the latent space. I've added in a bunch of question marks because it's a bit weird to me now to call this K and V, but whatever the DeepSeek people want to call it. And that latent vector is indeed shared across all heads, right? So how does that compare to what we've got here? Well, it seems like this multi-headed latent attention gets you high memory efficiency because you're sharing a latent projection across every head, and its performance seems to go beyond that of everything else. So, which is pretty neat. And if we substitute in real numbers, multi-headed attention on the DeepSeek R1 architecture, that's going to get you 4 megabytes for 1 forward pass, just purely in KV cache. Whereas multi-headed latent attention, I think that compresses things down by a factor of 60, and you still get slightly better performance. That's really quite impressive. So that's all well and good. That's kind of the attention mechanism optimizations I want to look at. Everyone is kind of focused on KV cache compression, a lot of other techniques and sparse attention. Yeah, a lot of things, non-exhaustive. Dense layer optimizations. I'm hoping that most of us are quite familiar with quantization. A couple of approaches here, right? Train your model in a float format, quantize it at test time. Pros, it's cheap. You only train your model once in full precision, and then it's a very easy thing to do to compress your model into, I guess, a confined number of levels. Cons, yeah, worse performance, because during the training process, you didn't factor in the fact that you were going to compress your weights. Quantization-aware training, which has started to become taken a lot more seriously in the LLM space. I think BitNet were probably the fanciest demonstration where they did binary and ternary language models. And they found that, sure, if you were to do post-training quantization, you're going to hit this kind of limit of accuracy where on the x-axis, you're reducing your bit width and of course your accuracy plummets. But if you add in quantization-aware training, then you go past that pre-to-optimal frontier, happy days. So with respect to quantization-aware training, you quantize weights on your forward pass while storing your full precision values. You apply gradient descent to those not necessarily full precision, or brain flow, half precision, mixed precision, whatever you want. Problem, it's less cheap. You can't generalize to various hardware if they're going to be taking advantage of alternative quantization factors anymore. Int 8 needs its own quantization-aware training. Int 4, float 4, whatever, needs its own. So less cheap. Finally, I wanted to talk about system optimizations. I kind of think of these as agnostic to transformers. You can really apply them to whatever the fuck you want. The first one that I want to show you is mixture of experts. And I guess really what that's answering is, how do we scale up architectures to larger sizes without scaling up inference compute? The answer is build a larger model, but don't use all of it at once. Use more memory, you have more information about the world around you, but don't use it all at once. Now, what that entails is usually taking this feed-forward projection, that bottom row, clunky, many upward and downward feed-forward layers. We take that, instead of having an input with a residual string to the output, we subdivide it into what are called different experts. Now, it shouldn't imply to you that one expert is truly an expert at anything. My hot take is that these are just distributed representations that accidentally became good at something or other, right? So we have a set of experts. How do we choose which one of these experts to flow through? That means you introduce a single mini little dense layer. In this case, every expert has a single neuron attached to it, and the input comes in, and those 4 neurons will tell you, hey man, I'd really like to go into expert 1. Expert 4 is pretty chill as well. We might trust that as well if we so desire. If we want to activate 2 experts. For now, let's just assume we're going to activate 1 expert. And so we're going to take in our input data, flow it through expert 1, ignore the rest. And this is a very, big space of hyperparameter optimizations here. DeepSeek, for example, they subdivided to much smaller experts, but they scaled up the number of experts that they used. I'm not sure if there's any real formal guidance on what that ratio of total number of experts to number of active experts really is at the moment. The next one that I think is really cool is speculative decoding. So take in that OG sentence, the cat in the, and you pass it into a small model. And the small model, being a small model, might be kind of shitty. It will generate the cat in the hat sat on the hostage negotiation, whatever reason. Now, we're going to take that generated text, we'll pass it into our large actual LLM. That is going to be fed into the huge model. And that huge model is able to kind of decode everything 1 token at a time in that pre-filled sort of manner. And it's going to generate a set of this probability distribution for every single one of these tokens. You can identify the probability of those tokens all at once, all in one hit. And sure, the cat in the hat sat on that looks good. There's a high probability of those words occurring based on our large model. So we trust those. But then hostage negotiation sounds a little bit jank. We don't trust our small models. So we get rid of those 2 tokens, we get rid of hostage negotiation, and we just feed in the tokens that we have a sufficiently high confidence in. So we're able to kind of get, I guess, hat sat on the 4 tokens or 4 words out of one small forward, several forward passes on a small model, but 1 forward pass on a more chunky model. And that is also a very common technique employed by modern language models. Now, fuck me, we're definitely going to push a little bit past, but let me continue speaking at 10x speed. Modifying or replacing self-attention. So this generic depiction of what transformers look like, but we have token mixing. Why use self-attention? Why is self-attention the only possible option? Well, it's not. We can use recurrent neurons, but of course, we know that there's a lot of problems with recurrent neurons. 1D convolutions can also fit the bill. They are token mixers as well. They're mixing information through the sequence. So let me illustrate with a silly example as to what the problem is and what the fix might be. So those of you at Telluride last year might have seen this. Take the sentence, Andreas saw Toby with binoculars. My question to you is, who has the binoculars? Is it Andreas? Is it Toby? Right?
It's right.
What was that?
This is a garden path sentence, huh?
Exactly, right. Cornelia. So linguistically speaking, it's ambiguous, right? Andreas could have seen Toby with his own binoculars, or he's watching Toby who happens to have his own set of binoculars. But with a bit of context, we're humans, we're not too stupid. If Andreas saw somebody else, quite probable that he's the guy with the binoculars, right? Now, if I was to pass this into a transformer, every word has its own embedding, we generate a self-attention matrix. That self-attention matrix finds the relationship with each of these words with every other word. Now, in attention, you have, in principle, perfect memory, right? Every token is stored in the form of your KV cache. And we're lighting up the link between Andreas and binoculars because attention has access to the full context and it can say, cool, there's a high value between these two guys because I have perfect memory. So in this case, we see memory grows quadratically with increasing sequence length. But in the case of RNNs, you're going to start fading information. You're going to lose a lot of information about Andreas by the time you've reached the token of binoculars, right? Vanishing memory. So that is really one of the primary issues with recurrent neurons, with state space models. So let's take in the most generic expression of a state space model where the time derivative of x is equal to some, could be a scale, it could be a vector, it could be a matrix, a of times x plus b times u. This implies that x is some state and u is some weighted input, all well and good. If we were to run the forward Euler solution, then we might get this discrete time alternative where the state at your next time step is equal to some factor multiplied by the previous hidden state, and we add that to some weighted input. RNNs are very slightly different. The only real difference here is that there's some nonlinearity applied to that hidden state before updating the next time step's hidden state. And I want to bring up this animation of what a leaky integrating fine neuron might look like, where you might apply some input current, generate a membrane potential jump, which exponentially relaxes. That is a state space model if you ignore the reset mechanism, because the reset mechanism is a function of some spike, which is a hard threshold. A hard threshold is a nonlinearity. So if you ignore resetting, spiking neuron, leaking integrating fine neurons are a discrete time solution of a state space neuron in the way that we use them. So memory complexity in this picture no longer scales with sequence length for inference time only, right? As I extend the time window that I'm processing, I do not extend the amount of states that I have. Attention grows the amount of states you have in the form of a KV cache. Here, I've just got one number. That number is all that changes, nothing else. So memory is efficient in that way. But it also kind of sucks, right? That's why we had to push over to self-attention. So what do we lose? Sequential inference or training, right? We've got to go through this for loop to be able to process everything one step at a time, even during prefill. Lack of nonlinearity means that we no longer have this universal function approximation kind of magic that neural nets have imposed in RNNs. There's also n-cubed complexity in matrix multiplication if A is a matrix and if Q is a matrix state. And finally, you also get shitty long-range performance. That is probably the main killer of using sequence models. So how do we address all of these, right? Let's look at sequential inference to start with. So this equation is fundamentally recursive, right? We run this equation through a for loop in order to solve it. However, if we assume a linear time system, then we get a closed form solution, right? Closed form solution meaning that if I have a single input here, I know that the response is going to be some exponential kernel. I can just plug in, some vector that sweeps from 0 to 100 time steps, plug that vector into an exponential function because I know that the solution of this equation in continuous time is going to be exponential, right? And I just do that for every single one of these inputs. Then you end up with a bunch of exponentials that are distributed through time. You add them together in that tree-like parallel scan-esque manner, which scales with log t complexity. So you're able to get around it, assuming that you use a state space model. This nonlinearity in RNNs in the way that they were kind of postulated in the 80s does not give you that closed form solution luxury to be able to train things fast. If you can train things fast, you can train on a fuck ton more data. That is basically what lets you do things that resemble language modeling. So that's all well and good, but then we're trading something here. If you remove the nonlinearity, then you screw yourself over with respect to the universal function approximation theorem. How do we get around that? Well, we take, so we address the first one. Let's go to the second one. Well, we take that nonlinearity from the RNN case and we do the dumbest thing possible and just push it out into what's known as a positional nonlinearity, where the if we say that we have a linear token mixer, that is a state space layer, and we concatenate it with a nonlinearity at the input and nonlinearity at the output, then we're able to kind of win all the benefits of universal function approximation. You get that representational capacity back without having to have backprop through time or sequential processing with the channel mixers. And so the start and the end are just feed-forward layers, right? The complexity does not scale with time. The token mixer, that's a state space model, so you go back to log T complexity, and you still preserve nonlinearity, just apply that in the linear layers, right? That's it, right?
Do you need some sort of constraint between them, so they are inverse of each other, or that?
There is no constraint.
Just
Yeah, I think there are a couple of papers that have proofs that I honestly do not understand. Yeah. So that's all well and good. The next is this n cube complexity. Because yeah, if A and X are matrices, then yeah, you're going to have to do matrix multiplication. I'm not going to go through that derivation here. I showed it last year, but effectively, there is a world where A can be diagonalized, and if you can diagonalize that matrix, you can compress it into a vector and do element-wise operations on that vector. And as long as you have that channel mixer, the nonlinear channel mixer at the start and at the end, then you win back all the benefits of matrix multiplication. When I say benefits, I mean the representational capacity. And go through that in a lot more detail one-on-one if you hate yourself that much. The more critical issue is poor long-range performance. So let me illustrate this, right? We'll go back to our sentence of Andreas nefariously watching Toby for whatever reason. Now, if I was to run this through an RNN, let's say that this first spike represents the word Andreas, then by the time we've reached binoculars, you've kind of exponentially decayed and lost all information about Andreas by the time you reach binoculars. So in this naive kind of toy example, all information about the start of my sentence has just completely fucked off by the time I arrive at binoculars, right? That's a bit of a pain, right? And that is why people migrated away from recurrent neural nets, from sequence-based models over to self-attention. So we've got this case where attention is powerful but expensive, whereas RNNs or state-space models, they are cheap, but fuck, they're weak, right? How do we kind of balance all of this? Cornelia is very disapproving of my Australianisms.
Honestly.
You should just don't upload it. So
Cannot, honestly.
excellent. It is what it is.
Censorship from NSF.
Let's keep pushing forward. So
The INC word.
yeah, use that. Anyway. We've got this linear operation, right? We've got this linear operation, and you accidentally get some level of long-range performance for free because if you apply sigmoid to tan h, then what that kind of looks like is this is your forward pass activation, this is your derivative on your backward pass. As you go towards either end of that the backward pass, you're ultimately going to have vanishing gradients. So if you have linear operators, you already get some level of, I guess, you address vanishing gradients to some degree for free. That's one of many things that are here. Next, complex value transition matrices. So if you treat A as a complex value with a real part and an imaginary part, then you have the option of getting oscillatory decay. So instead of just having some exponential relaxation, you can effectively introduce oscillations into your process. In that way, Andreas is at the start and then it oscillates back up by the time you've reached the end of your sentence. So it kind of brings information back from the dead. And if you want to link this back to modern transformers, it's basically a recurrent variant of rotary positional embeddings, ROPE, right? Now, there's also data-dependent decay or forget gates. And this is probably the biggest key for enabling better performance with state-space models, where this, I guess, transition vector matrix scalar is an input, it is a function of your input data. For whatever reason, that helps boost performance significantly. Whatever reason, that's how forget gates work. LSTM showed it back in '96. I'm not going to go through this toy example of how to learn how to forget and whatnot, but the intuition is that if you have a constrained amount of state, if you have constrained memory that cannot grow with time, you got to get rid of something. You get rid of shit that doesn't matter in order to make space for things that do matter. Right? And then we go from this world where attention has too much information and RNNs have the correct information, ideally, right? And finally, and this is a bit more emerging from, say, the past 8 months, test time training, right? Test time training alludes to this idea that the hidden state is now a function of a local loss that aims to reconstruct a projection of information from previous time steps. So gated DeltaNet introduced this. I'm not going to go into low-level detail on this, but just think of it like this. You have some projection from a previous time step, and you're trying to reconstruct it during inference using some localized gradient descent, right? That doesn't make sense, don't worry about it, but that's the state of the art in SSMs as of today. So we've addressed poor long-range performance using linearized recurrence, complex value transition matrices, data-dependent decay, and test time training. What I see in practice are that these two highlighted red, linearized recurrence and data-dependent decay, are the most commonly utilized techniques out there to extend memory, but test time training is a little expensive, but it does bring back performance in long context benchmarks. So with that all being said, all of these are addressed. I'm going to fly through LLMs on neuromorphic hardware. Where are we at? You know what? I'm going to give you the, for those of you that want to piss off, I completely understand. Is the room free for the next 10 minutes?
Yes.
Yeah. Okay.
Yeah.
If you want to bounce, go. Everything from here, less tutorial, more about the work that we've done, Steve's done in order to make things work better. Won't be offended. You're all feeling stomach. All right, so go if you need to. Matt, what was that? Okay, so this matrix multiply free language model, it was the first billion parameter model that was able to do language generation without matrix multiplies. We used a lot of the techniques that I've already shown you. We used deep quantization, ternary parameters, or if you take -1, multiply it by some incoming activation, that's just a bit flip into its complement, +1. And you end up with 8 to 10x less memory in doing that. Learning to forget, data-dependent decay. And we ran things on an FPGA to reach 13 watts at human readable throughput. On top of all of that, we did all of those state space. This is a state space model. We did diagonalization of that transition matrix in the way that I guess S4, S5 are doing in order to remove all of your vector updates, and everything is just an element-wise operator outside of that. So things work well. This is a curve showing performance as you allocate more flops, right? And we've run simulations across 370 million, 1.3 billion, and 2.7 billion parameter models, comparing matmul-free against just the canonical open source transform ++ variant, which is the backbone of all state-of-the-art open source models that use self-attention. And you'll notice that as you increase flops and as you increase size of your model, so in red, you have the matmul-free model, and in blue, you have the chunky, expensive transformer, the gap between these two starts to converge as your model size gets larger. That is to say, with ternary parameters, that gap is effectively going to get smaller. At some point, if scaling keeps on going the way that it is, then it's something like less than 10 to the 23 flops, which isn't that much in today's day and age of LLMs, then there is a point where those two things converge. And that seems pretty nice. So running this on an FPGA, because of course GPUs are not very good at handling ternary ops and element-wise ops, like where we're losing a lot of the parallelism advantages in self-attention. So running this on an FPGA in a somewhat unoptimized configuration, we reach human readable throughput at 13 watts, which is nice. The performance that more or less matches what you get from transformers. What I think is more interesting is what we got on Loihi. Now, this is not a spiking neural network, but as I mentioned, state space models are basically spiking neural nets, right? And while there is an activation sparsity that takes advantage of all the asynchronicity of Loihi or Loihi 2, if you think about the decoding phase, when you pass a token into your first block, that gets transformed into the second block, and at that point, your first block no longer has anything to process. So all that there is just static power dissipation from every unutilized block. So Steve led this effort in trying to port matmul-free onto Loihi, and these are kind of some preliminary results that we've got. On the x-axis, we see sequence length. As you go up, you're extending the context of your input. And on the y-axis, we have throughput in tokens per second or samples per second. Higher is better, of course. We're comparing the matmul-free of all sizes in blue against 3 variants of Transformer++. And truth be told, we're not doing that much better at that 1K window. Of course, as you grow, the attention matrix grows in size. And so that's when state space models are going to look better. But then their performance also kind of drags down for the long context benchmarks. But one thing that is not shown here, I mean, granted, we do win at some point, but one thing that I'm not showing here is factoring in energy, right? Energy that comes from data movement from KB caches that are no longer present in the matmul-free model. So to capture that, we've got this plot here, or this animation rather. On the x-axis, we have joules per token. Lower is better. We want less energy used per token generated. And on the y-axis, we have throughput per token. Higher is better. We want more tokens generated in a faster speed, right? And the size of these green blobs represent the amount of parameters in the model. And so what I'm showing you is the comparison case, Transformer++, not a state space model. Down here is a 2.7 billion parameter model. Up here is a 1.3 billion parameter model. And to show you where matmul-free sits, I need to play this video that zooms out. And yes, this is the sweet spot, high tokens for low energy. That's where matmul-free ends up, which is really nice. 1.3, 2.7 billion parameters. But one thing that I've kind of hidden from this is that the transformer plus case, that's running on BrainFlow 16 values, right? Here, same number of parameters, but they're all ternary, right? 8 to 10x less memory. So if we normalize to that, then effectively the amount of memory used by these models grows significantly. So we're doing a lot better at the same level of language model benchmarking with a lot less. I think that is really powerful. I'm not going to go through these kind of actual real demos of energy and whatnot, but to finish off, I want to talk about the next step of where language models are going, right? How do we get small models that perform on par with large models? And I've shown you that in the case of state space models, and reasoning hopefully generalizes to everything that I've discussed so far. And what I want to show is this idea that we're working on called recurrent reasoning. The thing is that if we've gone this far just to be kind of on par with industry's worst models, as academics, that's nice, but as someone that wants to be useful, bit shitty, right? How do we get a little bit better than that, right? A quick 101 to reasoning. I like to classify these into two parts: serialized reasoning, parallel reasoning. In the case of serial reasoning, imagine you have some input prompt, you chain that, you concatenate it with some other prompt injection that induces the reasoning process. That might be break this down into smaller steps. Then you just take the output, feed it back into that large LLM again and again to refine the answer, right? That's a very serialized and quite recursive operation. On the other hand, you might have parallelized reasoning where you take an input and you generate a bunch of samples using, I don't know, I guess probabilistic sampling of your output embedding. Now, in that case, this can be very useful. You then might go through all of the possible candidates of outputs and use a beam search where the beams are just the various candidates in order to find the value, the sentence or the passage with the highest cumulative probability. Because of course, the next most likely token doesn't represent a sentence that has the highest cumulative probability, right? And that starts to feel a lot like RL, where you have very much deferred rewards. In practice, these two things are typically combined in that chain of thought kind of process. Now, with OpenAI, with ChatGPT, we believe that a lot of this is happening in the token vocabulary space. So you're operating on actual interpretable words. Not sure about that, given that it's a closed form model, but we've been applying this to latent spaces, ideally language models do most of their operations in the latent space, right? So why project it outwards into text? Interpretability is great, but you're losing, I guess, efficiency from that. And what we're observing, this isn't our plot, this comes from another group who published to ICLR, where on the x-axis, as you go further out, you allocate more flops to your process. And on the y-axis, you have, I guess, decreasing error. The idea is that the more computation you allocate to certain processes, the better you do, right? I have some problems with plots like this because humans don't necessarily behave like this. You don't allocate more flops to everything. So a very silly example is, hey, what's the answer to this? You've got to take 4 or 5 seconds to count the number of 2s. I can simplify this down, and then now suddenly it takes you 0.5 seconds to figure out that this is 128. So there's certain things that are muscle memory, or I don't know, something that are just there in a lookup table, and there's certain things that you have to think about, kind of like type 1, type 2 thinking, as per David Kahneman's, I guess, hypothesis in thinking fast and slow. And in the same way that I think OpenAI are doing this as well, right? You've thought for 10 seconds based on the complexity of your input prompt. So we don't know what OpenAI are doing, and I'm not claiming to have reverse engineered what they've done, but we've done something that does take advantage of this dynamic length of reasoning. I think that this is quite powerful. And the idea is very simple to express at an arm's length. But imagine you have some output neuron to your LLM. And all that output neuron is doing is telling you, keep reasoning, or no, we're good, stop reasoning. You can think of it as like an early exit neuron, and it's very cheap to kind of calculate, right? We'll call it a recurrent router, and you can appreciate that if the recurrent router keeps saying, yeah, keep reasoning, then you end up with deeper reasoning steps, more recurrence in a way. But then there's a problem with that because fewer training samples are going to make it this far. Keep in mind, this is the same model. This transform token is going through the same thing again and again. And so when you run backprop, you're going to have a disproportionate number of samples trained, assuming that there is very little reasoning, as opposed to things that have very deep reasoning, right? And this is actually quite familiar because Mixture of Experts has this near identical load balancing problem. That is through space, this is through time. And so fixing that, we could do what the MOE people did to address load balancing, that is throw in some noise injection, great. An additional thing that we apply is we effectively combine RL with some reward that looks like an RL-driven reward. It's like DPO type of thing, which rewards extra exploration. right? Where n just refers to the number of steps. Don't worry about the exact math, but no, we're just rewarding more exploration here. And in doing that, how does everything stack up? We trained this not on a state space model, rather transformer plus, your canonical, simplified, very vanilla transformer. We compared it to the state-of-the-art models. We are still training. Right now, we're at 1 trillion tokens. We're blasting 256 A100s at a time. So these are from checkpointed results from 1 trillion tokens. It's a disgusting amount of computation going on. So the number of parameters are all in that 1 billion to 1.5 billion ballpark. Now we're only at 1 trillion. Llama 3.2 is 9 trillion tokens, a lot more. QN 2.5 is 18 trillion tokens. So they're far ahead of us in terms of compute. The average accuracy on benchmarks that somewhat do matter, Arc Challenge, MMLU, things that people care about, look something like this. We're completely dominating Llama 3. And QN 2.5, we are just slightly behind them for far fewer tokens of training. They're not doing reasoning, of course, but they are also fine-tuned. They've done SFT, they've done their own shit to make it more optimized for, I guess, use as a chatbot. Us is purely pre-training while combining this thing that looks like RL, right? And there's this one additional ablation study that I thought was extremely important to run, and that is, does this dynamic varying depth of reasoning matter? Should we just allocate the maximal amount of reasoning steps instead? And will we always do better? And the answer is no, right? We got this from a 100 billion token checkpoint, where on the left, you see fixed depth reasoning. We maxed out at 8 reasoning cycles. And on the right, we let the model early terminate all of the reasoning steps. And you find that, I guess, by using less computation, you end up doing what I think is considerably better than the case where you maxed out your reasoning steps. And that kind of shows that those generic plots where extra compute means lower losses don't generalize to most things. So this is a beautiful way to show that, this brain spy computing is almost like a behavioral thing now, going up the stack and all that, which is kind of interesting. So dynamic reasoning effectively enables 1 billion parameter models to perform at the level of 8 billion parameter models and those that are trained on so many more tokens. I think that is pretty damn nice, getting to state-of-the-art industry level models within academia. So with that being said, none of this work is possible without the incredible PhD students in my lab, in particular ReJ, who led a lot of the work on SSMs and reasoning. And also a lot of this work was also done in collaboration with Steve, who really did a lot of work. He led the effort of compiling Matmore3 onto Lowy. He put an insane amount of effort optimizing that. But with that said, get out of here. We can do Q&A. People can leave if you need to go pee or something.
Okay. Hello, everyone. Today I'm going to be talking about some work that I've done and also work that other people have done on integrating symbolic reasoning and also representations in LLMs. So the motivation behind why we want to do this is that obviously, as Jason pointed out in the last tutorial, LLMs are extremely powerful pattern recognition models, basically trained on the entire internet, to compress huge amounts of data into weights. Functionally, they align more with system 1 capabilities of the brain, which have advantages and disadvantages. So for example, they're extremely robust to noise and also relatively fast compared to system 2 processes. However, they're also error prone and struggle to generate data out of distribution. Contrasted to that, symbolic reasoning aligns more with system 2 thinking, which is deliberate, slow, it's verifiable. However, it also requires precise inputs, which is why they haven't scaled to the level of large language models and those kind of approaches. So this work aims to bridge this gap by converting LLM hidden states into interpretable neurosymbolic vectors, basically VSAs, which are used by symbolic algorithms to steer the LLM during its forward pass. So before I dive into our work, I want to talk about other approaches that have either attempted to decode the LLM's internal state to find out what it's thinking, or have attempted to improve reasoning of LLMs via different search-like approaches. So the first work I want to highlight is linear probes. So the way that linear probes work is that they convert LLM hidden states directly into a limited set of symbolic representations. So in this example, on the right, we have work that's converting LLM hidden states when prompted with mathematical problems into symbols that represent the digits that the model is being presented with. So essentially, they're training one linear weight matrix for each symbol that they want to decode from the LLM hidden state. And this work this approach works relatively well, but there's a lot of limitations. So for example, if you want to add new symbols that you want your model to recognize, then you need to train entirely new encoders to do so. And also the process is supervised. So we are kind of inferring something about the way that the LLM represents its internal states just by structuring our network during training. So a potential improvement on this is sparse autoencoders. Sparse autoencoders are an unsupervised method of claiming the internal thoughts of language models. And the way that they do this is basically you have the same LLM hidden state and you project it via a weight matrix onto a set of activations, which you enforce to be sparse by different modified activation functions, as well as L1 norm laws. And then you linearly project those back onto a reconstruction of the original LLM hidden state by a decoder network, and you train for the reconstruction loss of the original state. So this allows you to do some interesting things, like a common example is Golden Gate plot. So one of the sparse activations in this SE that Claude, that Anthropic created, relates to the Golden Gate Bridge. So you can actually clamp this activation to increase it, even when the model is not supposed to be thinking about this topic. And the result is, if you ask it any question, it will pivot towards the Golden Gate Bridge. So for example, you ask it, what's the highest calorie food at McDonald's? It responds, the food with the highest calorie count at the Golden Gate Bridge is the Golden Gate Bridge itself, which contains around 1.6 million calories with the steel cable. So yeah, eventually it steers back to talking about the calorie count at McDonald's, but yeah, so there are different applications, potentially narrow applications, I guess, but yeah, it's kind of a cool method to figure out the LLM is thinking. The weaknesses are that a lot of manual intervention is required to figure out what these sparse activities actually mean. Often people will run different prompts to the model and then record which activities light up in the sparse layer to figure out this sparse activity corresponds to these concepts. Another disadvantage is that every time you retrain the model, there's no guarantee that these activities will be the same. So they're not like universal concepts that you can obtain from the model. And also, they're not necessarily monosemantic or atomic concepts. So for example, the Golden Gate Bridge is not really an atomic concept. It's composed of different ideas like the bridge, San Francisco, etc. Okay, so one way that people have tried to improve on SAEs is that they've trained cross-layer transcoders. So these functionally are similar to SAEs in that they reconstruct hidden states of language models with via sparse activations. But cross-layer transcoders are trained to reconstruct different layers of the transformer. So, for example, if you take the first, if you generate a sparse activity on the first layer, it will be trained to reconstruct the NLP or the hidden state at future layers. So big advantage of this is that it can give you some insights into the algorithm that the LLM is running during its forward pass. For example, concept about a number here could influence a different concept about a different number in a future layer. However, because you're trying to do a more complicated task of reconstructing future hidden states, the error is often a lot higher. And so what people often do is they put error correction nodes into these models, which kind of hurt the interpretability because those error corrections are basically forcing the hidden state back to what it should be. But we don't know how they're doing that. So yeah, there's definitely trade-offs. Regardless,
So the
yeah.
features you have, now you interpret them as algorithm or functions instead of concepts. Is that it?
No, these are still concepts. So this is still a sparse activation.
Yeah.
But instead of reconstructing this MOP or this hidden state, you're now trying to reconstruct the hidden state of future layers.
Yeah.
So the way that you get functions is just by looking at the activations of different layers and kind of drawing, like for example, if a particular activation in a lower layer is active, and it has a high influence on another layer, then you can kind of figure out that, okay, this activation is important for whatever computation is being done in this higher up layer. Yeah. So yeah, a lot of researchers, specifically Anthropic, have used cross-layer transcoders to create what are called circuit tracing models or attribution graphs. So the way that this works is that you start by creating a replacement model. The goal of this model is instead of running your forward pass on your ML via your self-attention and NLP, you now keep your self-attention, but you use the cross-layer transcoder to reconstruct hidden layers at future states. Right, so yeah, the rest works pretty much the same as the cross-layer transcoders, but the additional aspect of this is that in order to figure out how the activations of the sparse layers in previous tokens affect the activities in future tokens, you need to basically look at the attention scores of your frozen self-attention in your language models to determine how certain activities flow into future tokens. So yeah, like I said, the advantage is that you can create an attribution graph, but the disadvantage is that it doesn't tell you how the model is generating these attention scores. Whereas Jason was talking about in his last talk, how the model is doing this mixing between different tokens and different hidden states. But still, we can address like a large variety of algorithms the LLM might be able to run just with this setup. One example that Claude has on their website that you can also go and interact with to see how exactly the model is decomposing individual tokens into different features is this example of addition. So here you can see we're presenting the model with two different numbers, and each of them are being sort of decomposed into features that represent, for example, the tens place and the ones place. However, you can see it's not like an exact science because the way that 36 is decomposed is different than the way that 59 is decomposed. And then on top of that, the features that are being activated are not necessarily sort of the canonical way that people would do addition, but this sort of fuzzy logic way of doing addition. Yeah, and the activities here just generally represent the concept. So on the x-axis would be the first number, and then the y-axis would be the second number. So this represents the space of all possible numbers that sum to 92. Yeah, so this node, for example, would activate on different mathematical addition problems as long as the sum is 92. So yeah, basically this is an example of how LLM might be doing addition. The thing to note though is that there's a lot of manual intervention here where the people at Anthropic are sort of grouping different features together and eliminating other features that that don't sort of fit into a nice narrative. You can actually go on to Neurosymbolic and construct your own attribution graphs. And if you do, you'll get something more like this, which is this much noisier, complicated system that shows you how the model is going from two numbers to a solution. And there's a lot of caveats as well. Like, for example, this final activity for 8, we can trace what's influencing it and why it's has a high probability. One of the things that's influencing it is this node that corresponds to, say, the number 8. But this actually has a negative weight attached to the logic. So that's kind of implying that the fact that this state is on is sort of depressing this neuron rather than activating it. So there's a lot of like sort of small caveats here that are sort of glossed over in the Anthropic paper. But regardless, it does give you a lot of cool insights into how, you know, how these LLMs might be performing these algorithms. And the nice thing about this is that this is open source, and you can go and provide your own prompts and see what kind of circuits the algorithm is making. And if we have time after, I can walk through how to use that system. So I also want to touch on these methods that are sometimes called deep learning guided program synthesis. So approaches like DeepSeek-R1 and O3 effectively traverse a domain-specific language, which is defined by your tokens, during learning and inference. So for DeepSeek, it does it during learning. And the way that it does it is basically, given a particular prompt, it generates a set of possible answers or trajectories. It acquires a score or a reward for each of these answers. And it learns like reinforcement learning to traverse the paths with the best answer. So it's kind of doing its program synthesis or search during training, and then during inference, it just follows the best path. Methods like O3, we obviously don't know exactly how they work, but we do know that they're able to do some kind of search during their inference. So this is essentially using test time compute to traverse different possible answers. Some weaknesses of this approach, though, is that because the DSL is fundamentally at the token level, the search space is extremely large, and it's not always intuitive for every problem to use this token DSL to do your search. So, for example, this is the ARC-AGI test, or the ARC-AGI benchmark. And if you're not familiar with it, later in my slides, I'll have an example of it. But basically, it's a reasoning benchmark. And you can see that a lot of these models do not so great. Human performance is around like 90%. O3 does pretty good, but it uses $3,400 for every inference pass. So it's coming at a huge cost of doing this search space in real time, or doing the search in real time. And they've also released a new benchmark, ARC-AGI2, where all these models are really bad. But those are just more difficult problems. Okay, so now I want to talk about our approach to try to address this problem. So the layout or the format of our experiment is going to be prompting the LLM with different sets of mathematical reasoning problems. And we're going to train an encoder network to convert the hidden states of the LLM into vector symbolic representations. So in this sense, this is a similar approach to the linear probing method. Then we're going to run some kind of symbolic algorithm on it based on the question being asked, and then decode that result in VSA back into a hidden state representation that can effectively steer the LLM. Right. So these are the format of the types of problems that we're asking the model. In order to make the questions complicated enough that the model doesn't already get them as it's pre-trained, we're making them 3-digit numbers. And our base model is llama 8 billion, so it kind of struggles on most of these. And during training, we're asking the model to produce the output in a single forward pass. So we're really testing what kind of algorithm that the model is running in its forward pass, not necessarily during this chain of thought, or kind of like you could think of as program synthesis in the token space. And of course, we format all of our prompts in natural language. And yeah, as I mentioned, we take the hidden state of the most recent token in order to pass through our encoder. So to answer the question of why we want to use VSAs in this particular problem, to represent this sort of mathematical structural problem, the fundamental issue we're trying to solve is the binding problem, which is about linking features to their correct objects. Neural networks traditionally don't do this very well. However, attention improves this by helping them to relate elements within a sequence via the self-attention mechanism that Jason discussed. However, it's important to note that this can only be learned during training, and it's more or less fixed and sort of embedded into the weights of the model. So could be a potential reason why LLMs might struggle with out of distribution kind of reasoning. VSAs, on the other hand, have explicit algebraic representations or operations for creating these compositional representations. And they have the potential upside of working for novel combinations without retraining, basically in the same way that a lot of symbolic program synthesis approaches operate. So, yeah.
Sorry, just quick question. What do you mean exactly, like with linking features to objects? Like, what are features and objects? Is it features of different objects, or?
Yeah, so features of an object or different objects or something like that. So in this example, say you consider this natural language phrase, right? Of course, you could use an LLM, and it's seen phrases like this a bunch of times, so it will be able to, create vectors that effectively represent, there is a fox that's quick and it's jumping over whatever, right? However, you can also do this with VSAs by creating this compositional representation that allows you to sort of create a hierarchical description of whatever problem that you've been presented.
How do you learn those representations from?
In VSAs or in
VSA?
Yeah, so I mean, this is exactly the problem with symbolic approaches, right? Is that they're very brittle and they struggle to be generally learnable. But that's kind of what my approach is going to try to do. It's going to try to learn these representations, albeit in a limited scope, but as a starting point. Right. So we're going to use the same concept of VSAs implemented in HRRs, or holographic reduced representations, which basically mean we just use circular binding, circular convolution every time there's a binding operation to define a VSA that encompasses our problem. So yeah, like I mentioned, we're going to provide the model with different types of arithmetic problems, and we can use VSAs to compose these into a format that maybe is more natural for people and algorithms to interpret. So we decode, for example, the hundreds, tens, and ones digit of each number provided to the LLM, as well as the problem type the LLM is trying to solve. Yeah, so we randomly generate a lot of these hypervectors. Some of them we can compose within themselves to sort of reduce the number of hypervectors we're randomly generating. For example, the hypervector for 2 can be represented as 1 bound with 1, so that we don't have to have like 10 different hypervectors for all of our digits. Yeah, and so on. So the first stage is do this pre-training of our encoder and decoder network. So this is as I mentioned, a supervised process. We are training this encoder to get in this hidden state of the LLM, reconstruct that VSA that I just showed on the previous slide. And then we can also pre-train our decoder to get in this exact same VSA that was just generated by the encoder, reconstruct the hidden state of the LLM. And we expect the decoder loss to be higher than the encoder loss because there's obviously more contextual information in the hidden state than just the symbolic representations of the input numbers and the problem types it's trying to solve. For example, there's information like what language was this question asked in, like what context, like are we adding apples or just numbers or something, like all kinds of different contexts is represented in this hidden state. But the decoder does its best to reconstruct that in the pre-training phase. So we do this training of an encoder and decoder at every single layer. But in order to determine which is the best layer to perform our intervention on, we can plot the loss of the encoder and the decoder at every layer. But mostly we focus on the encoder loss because if we can't accurately represent the input numbers being provided into the problem, then the symbolic algorithm running on those representations will be incorrect. So yeah, what we notice is that the encoder loss is minimized almost in the center of the LLM. The reason why it does this is like not an exact science, but like by heuristics, it's probably because the LLM needs a bunch of sort of self-attention applications in order to get a full context of the problem being asked. If you query the hidden state of the most recent token. And then we also see that both the encoder and decoder loss increase linearly or roughly linearly as a function of layer number after it's got its most ideal representation. So the reason for this is most likely because every time the LLM is running one of those layers that Jason mentioned in his talk that includes the self-attention and then the NLP layer. If you consider that as some function f, some nonlinear function f, each layer is computed by this function applied onto the previous layer plus the previous layer itself. So that's the skip connection. So that's kind of what allows these later layers here to have some like non-huge reconstruction error loss, because it still contains the information here, but it's been diluted by function passes over future layers. Okay. So, okay, we've got this encoder that can accurately convert hidden states into symbolic representations. And we've got this decoder that can kind of reverse this process. But we're not trying to just reverse this process because our goal is to get the LLM to output the correct answer based on our symbolic algorithm. In order to do this, we have to kind of carefully intervene in the forward pass of the LLM in a more robust way than just like telling the LLM to think about the answer. So in order to do this, we basically have a fine-tuning step where we run the encoder. So we prompt the LLM with questions, we take the hidden state, pass it through the encoder, run a symbolic algorithm, and then pass that to the decoder and only train the decoder at this stage and keep the encoder and the entire LLM force frozen. So this teaches the decoder how to effectively steer the LLM during its forward pass in a way that allows it to get to the correct answer. Okay, and then we also have the problem of when we query this LLM, when we query the LLM and get to the hidden state, convert it to a VSA via the encoder, how do we determine which of the algorithms to use? If you remember, there were 8 different algorithms, types of mathematical problems that we presented the model. So what we can do is we can find the similarity of each problem type with our dictionary of problem types, right? So we query the VSA from the encoder, we get the problem type, and we compare it to our dictionary. And because there would be, we're not trying to just train this LLM or the system to only do like these 8 operations that we trained it on. We wanted to not go haywire when presented with other information. We have a thresholding mechanism where basically if the query problem type similarity to all the possible problem types in our dictionary is lower than a threshold, in this case 0.8, then we will not intervene with the symbolic procedure. So we're basically guaranteed to not harm the LLM when we're not prompting it with problems that we've trained this algorithm for. But at the same time, we're helping it in cases where we're prompting it for problems that it's been trained to handle. Additionally, so this is with explain these graphs. This is a set of problems that it's been trained to address. So like multiplication, modulus, things like that. And then we have a withheld set of other arithmetic problems that we haven't trained the model to basically handle. And we see that there's a clear separation between these 2 distributions, and we can draw a threshold to separate them. Similarly, if we prompt them with non-math related problems, so for example, questions like about philosophy or psychology or something like that, the similarity of the problem, of the extracted problem type to any of the existing problem types in the vocabulary is even more different. So this is, I guess, good. It's just kind of a sanity check that our model will not be harming the LLM during other types of problems you have for it or other types of uses. And so to kind of compare our model to other benchmarks, firstly, we use chain of thought. So again, this is this kind of program synthesis approach where the model is creating an algorithm in tokens and then trying to execute it. And we also have LoRa, which is just a popular fine-tuning method because it's particularly because it's parameter efficient. Yeah, basically in our approach, we just replace the encoder and decoder with totally trainable weights and train it all with gradient descent. So the results of this, when tested on an unseen testing data set of 1,000 problems, is that basically our approach outperforms both chain of thought and LoRa, and obviously the base LLM as well. Chain of thought offers some improvement on many problem types, but yeah, we can go into all the failure cases of chain of thought in further detail if people are interested, but it's unable to increase the performance in the same way that the Neurosymbolic approach is. What's also important to note is that there are these, like I mentioned, 2 unseen problem types. So these are problems that we haven't trained the encoder to basically identify. So what we want our language model, or what we want our approach to do, is ignore these prompts and just use the LLM's normal forward pass. So that's why we see that the standard LLM, which is just the untouched LLM, performs about the same as our approach. And the only instances where it would be different or worse is because, again, of that this thresholding there sometimes falsely activate on problems it's not supposed to.
Just a quick question. So in this case, it seems that the unseen problems are simpler than the seen problems, right?
Yeah.
Do you have an example of an unseen problem that is also hard?
They're probably, I don't have an example here, but the reason I didn't test that is because basically what you would see is that the LLM does really badly and then everything does really badly as well, right? Mm-hmm. So it would just be like, here I kind of wanted to highlight that, approaches like LoRa, because they're supervised fine tuning methods, they change the model weights basically, or the parameter space. So it makes it worse. So if I did it on a like typical problem type, LoRa would be just as bad as everything else. So.
Sorry, but the VSA stuff only works, like it's kind of hand designed the algorithms, right?
Yeah.
Okay.
Yeah, currently it's hand design, and I'll get into future works as ways to change that.
So all the baseline that you have, they don't use any symbolic stuff. It's just pure neural network. Right?
Pure what?
Neural network. So LoRa, COT, and standard LLM, there's no symbolic stuff.
Yeah.
What about if you, let's say, take LoRa, but now instead of predicting directly the answer, you predict the Python program.
Yeah, so that's tool use, right?
How would it compare?
I haven't run that experiment, but I assume like even if you don't do LoRa and you just use a regular LLM and do that, then it would do like really well. All it has to do is reproduce the numbers, like pretty much reproduce the question. But again, this like the main focus of this approach is not just like improving performance on these problems, but also creating interpretable representations. And you'll see in the future works other benefits that could come of that can't necessarily come from using just tool usage.
Okay.
But yeah, it's a fair point.
Yeah, I think it's a nice question whether like in LLM we want symbolic representation inside or just outside.
Yeah, that's pretty much the question we're trying to ask, right?
Yeah.
And with tool use, the symbolic representations that you have that go into your program have to be tokens, right? Like by construction. Whereas here they can be more fluid and like for example with ARC that I'll talk about later, they can be more suited for image representation or something like that.
The chain of thought, and it seems like the LoRa even more, is really destroying the performance of the standard LLM. Is that something we should, on the unseen problems? Is that something we should be terribly surprised by, or?
You shouldn't be surprised by the LoRa reducing performance because it's been trained on these suite of problems. So it's expected. Chain of thought is kind of weird, like it really shouldn't be doing that much worse. So yeah, there's failure cases of that I can go into a chain of thought, like maybe it's because I'm using lambda 8 billion, which is not like a 400 billion parameter model, but it'll get into like loops of just doing addition and then going on forever and then failing or something like that. So
sometimes the models just kind of overthink it if you give them too much like reasoning space, right? Because if it's a simple problem, it can one shot solve it. But then you give it space to think, then it might do stuff like, oh, but maybe this is not the right answer. Like, oh, I should think harder, and then it messes up.
Exactly.
So instead of creating artificial intelligence, we've created artificial anxiety.
You should read the like reason or thinking traces from the DeepSeek models because they get very anxious. Sorry, go on.
Just curious, since with these representations that you can do some symbolic manipulations, like with the operations in the vector space, and so that's all differentiable. You thought about exploring that to like
Yeah, like so in my initial work, I started with addition and then I created a version of addition that was differentiable. But I think the pre-training stage of the encoder is quite important because otherwise, again, we just have this strange neural network where we don't really know if the intermediate states are interpretable or represent what we want them to represent. But yeah, I think that is definitely a possibility. And in the VSA cross attention type projects, I think it's more along those lines of having a fully differentiable function algorithm.
Python programming, you want to differentiate schools?
no, the symbolic algorithm on the VSA states, depending on how you design that could be different.
Okay, so you differentiate schools, symbolic programs, and you train everything as well.
Yeah. And like, yeah, so certain programs here are not differentiable, like if you just run it in Python, like the modulus or whatever, but there are ways to make it a differentiable equivalent with some error, of course. Right. Okay. So yeah, I mean, we could ask in this graph, why is it not at 100%? Because like it is using basically a tool or like Python internally. The main reason is because there are some errors in the encoding rate, or sorry, the encoding of the VSA. So we're not always going to be getting the correct digits from our problem. However, it is less than 2%, so it's not a significant source of these errors. The other source of errors is we have one linear decoding layer that's trying to steer the entire language model, which, by the way, the weights of the language model are kept frozen, so it has to learn this decoding in kind of a intelligent way so as to not totally derail the existing algorithm the language model is running. So this could also be a potential source of error, and there are different potential ways to alleviate that, like having multiple decoding layers, so that we kind of intervene on the language model at multiple points in its forward pass. Okay, so yeah, now I'll talk about next steps that we can do with this framework, because as you mentioned, like it's not like currently like application-wise, it's not that much better than just using tool use. But some potential things that this approach facilitates is drawing intuitions from LLMs. So instead of using the encoder to only represent the problem that was asked and running some algorithm on it, we can instead query sort of guesses or intuitions from the language model that we use to guide some kind of search process. So one example of this, and relatively simple example, is the game of 24, or the reduced game of 24, which is basically given two numbers, figure out some arithmetic operation to combine them to get a third number, right? So combining this with our approach, it would be just as simple as extracting an operation from the LM, whatever it thinks is most likely to solve this problem. And then, of course, if that works, we can extend it to a larger, the full game of 24, where basically you have four numbers and you have to combine them to get to 24 using arithmetic operations. Then there's more complicated problems, which, like as I mentioned before, LLMs currently kind of suck at solving. So the abstract reasoning corpus. In a similar fashion as the game of 24, we can query the language model for intuitions as to what it thinks the correct operations to apply to this particular grid are. Out of curiosity, does anyone want to try to figure it out before I say the answer? Basically, how to get from this grid to this grid using some kind of transformation that applies to both grids. So, yeah, or equivalently reflected towards. So yeah, and this is obviously one of the simpler problems in R. We could do like 12 by 12 grids and stuff like that. But yeah, this would be a good place to start to see if we can essentially do some kind of program synthesis to figure out what program gets you from here to here with heuristics guided from an LLM. Okay, then there's also the aspect of our training, which is that it was fully supervised, whereas approaches like sparse autoencoders are unsupervised and they give you representations for all kinds of different concepts. So perhaps a way that we can extend our dictionary of concepts that we fed to it during training are by presenting it with new problems and then seeing how those similarities align with the existing problems that it's seen during training. So in this example, yeah, we're querying the LLM with an integer division problem that hasn't seen integer division during training, so there's no VSA corresponding to it. However, we can see that integer division is quite similar to modulo and multiplication and not so similar to these. So perhaps we can construct a VSA that represents integer division using these as kind of basis function. Yeah. Okay. So I guess with the remaining 10 minutes, I kind of want to switch, not fully switch gears, but talk about a different potential application of this approach, which is, yeah, basically using the LLM to derive what to query from constructed VSAs. So the problem that the application that I'm want to run this on is visual question answering. So you start with a Scopus data set of different images. You run it through pre-trained segmentation mask. So I'm using mask deformer here. This will give you for each different segmented object, the area that it contains, as well as the label of the object. Then you can run also pre-trained language and image embedding models to generate high-dimensional embeddings for these different words and shapes. And we can finally combine all of that to generate one VSA that kind of represents this image. I would say this is one approach. There are other common approaches Nicole talked about in her talk. SS picture, I don't know if it's called something else, but basically you reconstruct this image as SSPs of the masks, so you can query them later for information about where those different objects are. Okay, so the way that I'm proposing to combine this with language models in order to get the language model to answer questions about these images is basically the same starting approach where we extract the hidden state of the language model at a particular layer. Then we pass it through an encoder to put it into the VSA sort of space. And then we project it onto these query and similarity vectors. So the idea is that this query vector will be bound with each object, and the similarity vector will be taking the dot product of that result in binding. I go here. In the example here, if we ask an LLM or some system, is there a tree in this picture, right? The way that we would figure that out with VSA operations is first we would unbind label. So it's equivalent to binding the inverse of label. So that would just extract this tree vector with some additional noise. Then we would take the similarity of that with the tree vector. And if that's equal to 1, that means that that there is a tree in this image. And if not, that means there isn't. So that's the sort of motivation for this approach of extracting that information from the model. So this will give us scores, which we can normalize with a softmax. And then we sort of scale the initial objects according to those scores and do a weighted average and pass it back to the decoder. The decoder here, again, its job is to convert the VSA representation of the solution into an interpretable form that the LLM can understand and steer towards the correct answer. So yeah, this is still like pretty initial work. I've got it to around 90% accuracy, but random guessing is like 50%. So, yeah.
So in this case, the LLM doesn't have access to the image directly at all. Like this is just a plain LLM with no vision.
Yeah.
Wow, that's cool.
This is the access that it has just to these VSAs.
Mm-hmm.
And yeah, there's definitely future directions that I want to try to improve this. First thing is the softmax is kind of just a sort of hack that I did to make it train well. Really, you don't want a softmax here because what this would imply is that the probabilities for these scores always add up to 1. But obviously, if there's no, for example, if there wasn't a tree in this image, then you would want the probabilities to add up to 0 so that it represents that here's a representation for that image.
What are the objects again? I forgot.
Yeah, so sorry. The objects are these things. These sort of VSAs that we constructed from these pre-trained models. These are all embeddings. So mask and tree mask, for example, are extracted from Dino and Roberta. Yeah.
How are those embeddings made? Like, do you just hand make them, or can you speed run them all?
These embeddings?
Yeah.
So they're coming from these pre-trained vision and language models. So I start with an image, then I segment it according to master former. And then on these segmented images, I pass the shape into Dino and the label of that into Roberta. And that's how I get those embeddings. Yeah. So yeah, ideally remove the softmax so that the scores can be all zero potentially. And then, yeah, we would probably also want to enforce that the queries and the similarities actually align with what we expect them to. I guess this is kind of what you were mentioning before, Nicole, where you have this full end-to-end train system, but what I found is that without some kind of error signal on what the output of this query is, it will just be anything, which still somehow gets to 90% accuracy, but it's not the interpretable VSA that we want it to be. So maybe adding a loss to force the output of this query to be, in this case, label inverse, might help the model train stably. But yeah, that's all I have.
Can it work if you have some stuff like is there 4 trees and 5 and
Yeah, there's often like multiple objects, and they can be repeating. Yeah. I just chose 2 for simplicity.
Thank you. So got some time for more questions if anybody has.
How would you scale this up to make it more generalistic? So what if you didn't want to just, what if there was like subcategories of your classes and then higher classes? Is it going to be hard to scale up, or do you think it would be general?
Well, yeah, it's a good question. I think there's different approaches. So you could just stack this multiple times within the same sort of symbolic part. You could take an approach that similar to what Jason was talking about, where you have the entire sort of forward pass recur and then you start back without decoding, so that you get like another activation of this process. I think there's multiple ways. I mean, you could also obviously decode into tokens and then do it again too.
For the like language only kind of a math question one, do I understand correctly that with the encoder, the encoder comes first, right? Yeah, with the encoder, you're trying to get both the kind of operation and the number.
Yeah.
So those, like, you have kind of 2 separate encoders in this case.
It's actually one encoder because this is just one high-dimensional vector. So
okay, because the problem type is bound within that vector to
it's bundled, so it's summed. But yeah.
Right. Yeah, okay.
Yeah, so that's kind of why this is in my opinion, a better approach than linear probes, because linear probes, if you wanted to add like, you started with just this and you want to add problem type, then you have to train another encoder to gather problem type.
Yeah.
Whereas here there might be ways of adding more representations.
This is very cool. So the encoder is kind of responsible for mapping from LLM representations to the VSA, and the VSA, are those just like random vectors then, like randomly initialized, each one of those?
Yeah, basically those are almost all randomly initialized. Certain numbers like 2, 4, and 8 are like pseudo randomly because they're like one bounded itself 2 times or 8 times.
Right, okay, with the number.
Yeah.
is it hard to learn an encoder like that? For instance, if I compare it to I just take the sentence that is written here in text. I took a sentence embedding, I try to predict it. How does it compare?
Sentence embedding with what model?
Whatever, LLM. And I'm just trying to see whether, like, for a neural network, so your encoder, how hard it is to predict this.
Well, so I will say it's a linear encoder, so it's not like doesn't have intermediate representations. I will also say we did test this on Llama 1B, and we got very similar results. In fact, the demo notebook that I have is for Llama 1B, so you can, I'll upload that and you can check it out. It's got slightly different like kind of version of the B-squares where the representation is the most accurate. It kind of like is the most accurate in relative, not halfway, but like 75% to the model, but yeah.
And the size of the VSA vector, it's the same size as the embedding dimension of the model?
I made it half as small, but you can make it Yeah, like I think there's just a hyperparameter choice.
Okay, because I was afraid it would be even bigger because you need like, big random vectors, right? For
Well,
the VSA, but
Yeah, I mean, the thing is that LLM hidden state already is 4,000 dimensional, so
okay,
yeah, like typically VSAs are like probably 2,000 dimensional or smaller.
okay.
Um,
Which is then really nice because then in the grand scheme of things of the LLM, the encoder decoder adds basically nothing.
yeah, it's like 16 million parameters.
Yeah.
So relatively lightweight.
Sorry.
Go ahead.
No, I was going to ask something. PSAs are obviously great and this is all of life's problems. But is it just the fact that you're imposing structure? Like, do you think it has to be these representation of these operators?
Like it's an implementation of VSAs or just VSAs in general?
Yeah, yeah. Like, I mean, so Tony Plate showed that you can do a lot of stuff with just like random wave matrices. And then just things wired up, take it away.
Yeah, like I don't really ask you the specific implementation of VSAs. Like the key aspect of this is that you can create these hierarchical structured representations where individual components of your structure are monosemantic. So like 0 means only 0, right? Whereas like in a sparse autoencoder or something like that, you wouldn't necessarily be able to find this kind of structure. You definitely wouldn't be able to because it's hierarchical. So this is hierarchical, so the SAs can't really do that. But yeah, there may be ways like that people are researching to make SEs more hierarchical and compositional, in which case it would be like, I guess, similar to doing this.
And you could, in principle, have like thousands, millions, and so on. Like you can just keep going to represent like numbers of almost arbitrary range, as long as you predefine it.
Yeah, and the way that the scaling of the error works, I have it in the paper, but I believe it's exponentially, you get exponentially more VSAs that you can represent as you increase your dimensionality.
Okay.
Just due to like sort of vector packing,
right,
in a sphere kind of rules.
So like if you were to replace this without VSAs, probably, I mean, like my first thing that I would try is like an encoder directly to some number representation, and that will always scale kind of badly, I feel. Have you tried something like this, like a no VSA comparison against?
You mean something like this, where like
right, yeah.
Yeah, basically you take the hidden state and you just project it to a number, right?
Yeah.
And then like you could do that, and people have tried and it works okay. But for every new thing you want to add, you have to create another encoder. Or like, start with a large encoder.
Would it? No, there would be no way if you train it only on numbers up to say 999, and then you test it on the number that has 1,000, because the thousands kind of vector is random, right? It doesn't relate to the 100 vector, or does it?
In this approach, or
in your approach in the VSA?
You could actually test it. Yeah, so I see here at the bottom that the digit place is itself like kind of repeated binding of the ones place. So tens is equal to ones, times with ones, hundreds is equal to ones.
Okay, so there is structure in it that the LLM could actually, or the encoder could actually.
Could, yeah. I haven't tried it, but it would be an interesting test to see.
That's cool. That's possible in the notebook, right? Yes, here we go.
Thank you so much for inviting me and for giving me this opportunity. It's a topic very dear to my heart. It's something I only learned existed like 3 or 4 years ago, and wish I knew way more about it. And there's so much to cover, so I'll only be able to do a very brief cursory glance. But it's very good to see all of you at Telluride. It's nice to follow everything on the sidelines. I'm curious just to hear a bit about your backgrounds. Like how many people have heard about dynamical systems before? Let's start there. Okay, awesome. How many people have background in, let's say, mathematics and physics? And how many have backgrounds in, say, computer science? and biology. Okay, yeah, good. Okay, I think I struck an okay balance. So my name is Jens. I'm a computer scientist. So yeah, that's my flag. And I feel like I will mention a few caveats here, right? This is a very, very broad topic. Like dynamical systems are massive. I'll try to focus on mathematical abstractions, also to give intuition, right? Because there are so many resources in this. So I'll just like mention some keywords, and if some of these stick, I've done a good job. Because then there are many, many more resources I'll mention where you can read more and learn more about this. I'll also focus on some biological motivation, just because I think it's important that we know why we're doing this, and specifically we work with neural networks. So again, I'll try to be practical and give you some math and codes, and the slides can be shared afterwards. It is important though to take notes, not just because you need them for later, but because that improves retention, right? So research shows if you write stuff down, you remember things. Good. So if you first just want to motivate the problem, right? I mean, biological systems use these dynamical systems in nature a lot, right? So a very important concept is central pattern generators, CPGs, and as they say, they're pattern generators. They generate patterns, and that's typically used for stuff like locomotion, because patterns for rhythmic leg movements or breathing or swimming are extremely important. And what's important here is that this is then a dynamical system that exists in isolation. There's no conductor or driver keeping these beats clocked. Right? If you're interested in this, I recommend learning much more about Yves Mader, who looked at some neurons in the lobster and learned a lot. I won't spoil the book, but it's very, very good. Neurons can also act as oscillators, and that gives you something like feedback loops and network interactions, and you can couple them together, and they give you very complex spatiotemporal patterns. So if you have like certain oscillators, you can put together, you can make one loop happening and then another loop taking over, and you can do that in many, many, many ways, and that gives you very, very complex stuff. Andy Keller was there at Telluride last year and talked about neural wave machines, and that's a big thing Terry Sanovsky believes in, because you can use the traveling waves across cortices to describe dynamics and capture memory and possibly some more complex things. But underlying all these beautiful ideas, we have to talk about the practice. How can we describe and understand and control these systems? So we're going to go through some tools to describe the dynamic, understand what you mean by a model of it, and then of course use that to predict behavior. And essentially that will help us design some control strategies and establish guarantees for what we want to achieve. Yeah, I will just briefly mention a quote here by this gorgeous book by Adrian and Shaw. It's called Dynamics, Geometry of Behavior, recommended to me by Steve. Thank you, Steve. Because they talk about how an organism is observed in different states, and this observed system is a target of modeling activity. Its states cannot be described by only a few observable parameters, but we can pretend. And the relationship between the actual states of the real organism and the points of the geometric model is a fiction, right? So everything we're going to talk about now is complete fiction, but it's useful fiction. I really recommend this book. It's extremely nice and very visual and intuitive. But that caveat just means that even when we talk about this mathematical ideal, right, it's not exactly how biology or the real physical world works, but it's a useful abstraction. Good, let's get started. First of all, we have to talk about state spaces. And state spaces are essentially ways that we can describe the dynamical system. So I'm going to assume that you're familiar with this notation. If this is weird for you, please raise your hand and let me know. Right? But imagine you have some kind of state variable x that changes over time with some function. And then you can read out the system. So the output of the system, the consequence, the action, is then some other function h, which then takes in this state variable. U here represents some input or control vector. So that's really the fundamental picture we need to get in place. We have a state, and that can be several variables. That state can contain many different things. We have some input, so that's where we control, we drive, we change the system, and we have some readout observation. So what I've prepared for you are some simulations here, because I think it's nice to get some visual input here. So you can see now this is running live, which is nice, and I can restart this. And if I present you with this dynamical system, well, it's not really dynamic, but kind of is where the output y equals the input. You can see this is a very boring thing, and if I change the input, the output then changes. Okay, so that's first of all an introduction to my way of describing these visualizations. I'm going to use a lot of them, but also a way to say this is how we can visualize states in the dynamics in the system. You're not visualizing states yet, right? There's no state in this. So we can then talk about a stateful system. So here's one example where the state x changes with some decay here. So as you can see, we start with 1, and then slowly decays down to 0. You can see the input right now is set to 0, so there's nothing kicking the system. If I add some kick to it, you can see, okay, it starts to grow again. But let's see what happens if I decrease the decay rate, for instance. Then the decay happens slower. It's probably hard to see. Faster. Yeah, slower if it's decreased and faster if it's higher, right? Because obviously then the system changes, right? So that's a good example of how a dynamical system works. And what's really important to know here is that there is a lag, right? Because of this, the state value here, in this case, the decay, any input will have, effect over time. And that's really what matters here, that the dynamics tells us quite complex, in some cases, dynamics, behaviors over time. So one approach to this is to find analytical solutions. And I just want to give you a rundown on how this looks like, because that's a wonderful way to get exact solutions. You can start with this equation. Let's take this decay, where you're deriving x over time, and we can separate the variables here. So now we just shifted x on the other side, and then we can integrate both sides. And if you remember your calculus, this is then the natural logarithm, and this equals the negative lambda decay rate t plus some constant. And we can solve for x, and this gives us the complete solution. So e to the power of negative lambda t plus some constant is basically the solution for this. And that's a very known equation. This is the leaky integrator, more or less. A lot of this and these kinds of way of thinking is described in what I call the Neuronal Dynamics Bible. It's written by Wolfram Gassner et al. And it's like a wonderful resource to know more about what happens in neural dynamics. I won't go much deeper into that. So some examples for state input and output for motor control could be joint angles for your state, right? Whereas your actuator in space. It could be velocities, right? And that makes sense because, if there's some momentum impedance on it, you want to capture that. And input would be some motor command. You can ask it to go to a certain angle or move to a certain position. And output would then be where the limb position is. And sensory, you can also imagine sensory feedback, but that's outside the scope for this. I'll just focus mostly on dynamical systems. So the state space is then the full configuration of the system. It's whatever you need to describe it. And a brief aside is on linear time invariant systems, because there's a very special class of systems which has a nice property that it overlaps with the convolution integral, which is basically a linear response. So there is some kind of response, impulse response kernel H, which you can convolve. You can apply that to the input. I realize I should have used a different symbol here over time. And the reason why that's important is because you have the superposition principle where you can take two things and it's linear. It's time invariant, so the system parameters themselves don't change, right? So if you imagine you have some constant in your system, if it suddenly stops becoming a constant, it's a little harder to work with. So these stay constant, and you can find analytical solutions for it. Because this is a linear system, there are obvious solutions for it. And the reason I'm introducing LTI is that it helps us to determine whether we can actually observe the internal state when we measure the system. And so if you imagine here, for instance, we have the system where X changes as some function of you know, this state matrix A, if you will. Then we have some input matrix B, and the output equally has some, you know, state matrix, but C in this case, because this controls the output, and D for then the input here. We can represent the observability matrix in essentially over different steps here. Like the first would be without any state applied to it; it'd just be the single C, and then we would essentially roll this A over time or in multiple steps. And this is important because if the rank of this observability matrix is n, corresponding to the number of states we have or number of variables in our state, then that means it's linearly independent. So each component is linearly independent. And that makes sense intuitively because if it's not linearly independent, then we simply cannot determine the system, right? There's no deterministic mapping. And then it's hard to determine the internal state when we measure it. Right? So for instance, in biology, right, if we measure some recording, like what can that actually tell us about neural state? That's hugely important for EEG signals, for instance, right? So you have to think about what you can observe. Another important point is controllability. So not only can we observe it, but can we steer it to any place we want to? So if you then here consider, you know, column matrix, and now we're only looking at the state here, where we're ascribing kind of the input B, and then connect that with the state matrix over time. You can, you know, forward that some steps, and essentially again we have that if the rank of this controllability matrix is the same as the number of variables, then it's controllable. Again, if it's not, then we don't have linearly independent. And if it's not linearly independent, then we're in trouble, at least in these LTI systems. This is dual to observability. So the reason why controllability is important is we have to ask ourselves whether we can influence the dynamics through stimulation. It doesn't make sense, you know, for me to wave at Michael if he's, you know, falling asleep, because he's not controllable at the moment. You're not falling asleep, Michael. You're good. So the reason this is important is because we can do sensory motor integration. So if it's observable and controllable, then we have a good case. And I'll just mention here, if you consider some kind of feedback gain matrix K, then you can work with the current state and the desired state and start to work with some closed loop control systems. I'm not going to go much more into this, but it makes sense for us to think about observability and controllability, because if you don't have that, we have to be clever. So let's talk about the leaky integrator. So here, let me restart this. We have a differential system where there's a time constant that's appended or multiplied onto the change of the state. So that basically means that every time we get some input I, and the state then changes by negating the previous value over the time constant, so to speak. So that means we're leaking some current. So let's put this down to 0. It's going to leak to 0. But the speed at which it's doing it is determined by this time constant. So let me try this again. Let me hit up a current at 1, for instance. And you can see it slowly reaches this. But let me now increase the time constant to 5, for instance, and then remove the input. So there's no kicking the system. You can see now it's relatively big time constant. It takes a long time to leak. So the longer the time constant is, the more you're splitting up, if you will, or you're subdividing the leak. Conversely, if you do it very quickly, you can see that the integration happens much faster. And this is very, very important for the timescales in your neural systems. Right? So these kind of plots are very important to understand how fast do these things act. And that's a big point I'll come back to later. Good. So here's just a very brief understanding of the leaky integrator. We saw the system here. We can separate the variables. So now we can see that the A matrix we saw before is basically -1 over tau. And the B matrix for the input is 1 over tau. And C here would then just be how we observe the state or the controllability, if you will, is just X. So that's trivial. So we can see that essentially we have observability and controllability under control. We are happy. DK integrators are good. Good. Yeah. So that's basically the
We have a question.
There's a question.
Jens?
Awesome.
Could you go back a few slides where you had like a takeaway slide that said like this is biological one, yeah, here. If you were to have neural recordings from the brain, in kind of an open loop setup where there isn't stimuli being sent back to the human participant, would you not have like a U term? Like if they're not embedded in a closed loop kind of paradigm?
So that's a really good question. It depends what you mean by your system, essentially. Right? Because if by the system, for instance, you're measuring some signal, right, then that could be the output of the system.
I guess for my context, I have neural recordings and I'm thinking that's X, or I'm
Yeah.
going to do some sort of modeling on that X on data
Yeah.
to get X's. And then Y would be the like intended action that we ask them to produce. Like speech, for example. So I'm wondering if I have a U term if they're not in a closed loop kind of experiment. Or would you like kill that?
Well, you can always describe this with these dynamical models. I think the question we should ask ourselves is it observable and is it controllable? And I would venture to say that in your case there are a lot of variables. I don't know how many, but it's more than 5. Just to pick an arbitrary number. So I think to your question, I'm not sure it is observable or controllable, but you can describe it. The question is, how good is your model going to be?
Okay.
Does that answer your question?
It's going there in that direction. Thank you.
Okay. Okay, I'll keep talking a little bit, but please feel free to ask me again. It's a really good question, right? And I'm happy you bring in some practical examples because hopefully this is supposed to be useful. Okay, I'll depart from the basics and talk a bit about optimization and stability because I think it's important to understand how we work with these systems. Now we can describe them. The question is, what can we do with them, and what is the boundary around what we can do with them? And I think I talk about optimization and stability because I think those are very important terms for for engaging with these kind of dynamical systems. And one thing that I like to think about when we talk about optimizing these systems is energy. And energy is a very, very nice term. You've seen this, if you're a physicist, you know this probably to your heart's content. But physical systems are essentially doing energy minimization. So imagine you have some kind of energy function, and you can basically think about the state change as going against the gradient of that energy function because you want to go in a direction of less energy. That might be a bit of noise, but this is basically the fundamental description for a lot of physics, neural network dynamics, protein folding, gradient-based learning, and so on and so forth. And you might know this again from physics because this is exactly the principle of least action, right? You're kind of choosing some kind of path, some kind of action, and the total cost of that, Lagrangian, should then be, or the integral of the Lagrangian should then be minimized, right? So that's really the point. And if you want to know more about this perspective, I really recommend The Theoretical Minimum, which is a very, very nice book. It's what you need to know to start doing physics. I think it has a very, very good intuitive way to go through these formulas. But it has, in my mind, surprising amounts of relevance to the neural network domains. And in general, I like the Pontryagin maximum principle to talk about optimality in general in these kind of networks. And in optimal control, for instance, you can think about the similar heuristic as the energy minimization. We just don't always want to minimize energy. We might minimize some other kind of cost, right? So if you consider this kind of Lagrangian or the running cost, whatever it is, with some kind of final target, you can you can then study, you know, the effects, and of course want to minimize this over time, right? So you just minimize energy or whatever else cost that you have. And so, yeah, very briefly, right, I'll come into adjoint variables in a second, but you can work with the Hamiltonian as an augmented cost function and then figure out what is then your optimality. And that's really the goal. And hopefully that's a little clear. So again, lambda, I'll get back to in a second what that means. But that was pretty much optimality, as in just going towards the least energy. That's pretty much the idea. We also want to talk about stability, because some of these systems might be very, very complicated, and they might be very important, right? They might control airplanes. I think Toby mentioned that a few days ago. And if you want to control an airplane, you want to be sure that it doesn't fall off the sky. So we want to prove some kind of stability. And with this energy formulation, that's kind of easy, because if you just imagine that you have some energy which is more than zero, then the change should just be less than zero over time, because that means you're always reducing the energy. That's a form of stability. And so here, V is then a Lyapunov function. It's just some kind of energy or cost metric again. And again, yeah, we want to dissipate energy. We want to become better and better. And so this works for physical systems. Yeah, but there's no systematic way to find V always. So that's a bit of a problem. And we know this in biology from homeostasis and equilibrium and population dynamics. And these things can be very, very hairy, as I'll come back to in a second. But the formulation, the idea here is very, very simple. Just make sure the energy goes down. It's the same for optimization. But I think what's cool here is that if you think about this Pontryagin maximum principle and the Lyapunov energy, you get robust optimal control. And so then they are optimal, robust, and stable. Good. So another nice way to approach these systems is not necessarily analytically, but geometrically. And that's what this awesome book, Geometry of Behavior, is talking about. Because we can use geometry to extract information. So if you think about not just the state against time, for instance, but the space of all possible states, then you can describe what's known as the phase space. So this is just a combination of all the different state variables. And if you imagine that plot kind of where you know, you have as many dimensions as you have states, each point would then represent this complete system state, you know, one situation, one configuration of your system. And trajectories then would be the evolving system over time. And there's a very, very nice way to show this with phase portraits, where you're showing the flow of the states over time. So imagine you're dumping into a dynamical system, and then you just track the arrow or the trajectory that happens as you move along the phase portrait. And so one example here would be of a system known as Van der Pol oscillator. I hope I'm pronouncing that correctly. If any Dutch people is here, you should correct me. But this is then, you know, a second degree equation. But the point here is that we can plot the position and the velocity, so two different states, against each other essentially, and we get this nice plot. And you can see time then is no longer an axis; it's just the dynamical system evolving. And I can then try to change this nonlinearity parameter, and then we get a bit of a different system, but it's still moving in this phase space. And the reason why this phase portrait is very, very cool is because you could do that for all possible combinations or almost, and you get these very nice arrow plots. So again, imagine I'm dumped into the system at some point, for instance, here. You can see my cursor, right?
Yeah, you see it.
Awesome. Then you're going to move in the direction of this arrow. Or here, you're going to move in this direction arrow. So let's give you a very quick intuition what happens. And you might ask the question, what happens if I'm dumped down there? I'll get back to that in a second. But you can see these trajectories then follow along the lines of these arrows. So for linear systems, again, we have a very general equation here where the behavior is essentially determined by the eigenvalues of this state matrix A. And so you get the characteristic equation, which I'm not going to go too much into. It's just the determinant of A minus the eigenvalues of the identity. And you can immediately get some intuition. If the real part of your eigenvalues is less than 0, you're going to decay. But if it's the bigger than 0, they're going to grow. And that kind of makes sense, because if they're negative, right, you're going to have this pull apart or pull together effect, like we saw with the leaky integrator. You're going to leak, the state is going to dissipate from the system. But if it's positive, it's going to grow out of bounds. And of course, because it's a dynamical system, nobody's stopping it, so it can keep growing. And you risk oscillations later. So it's important for me to say, for nonlinear systems, this is it's a bit of a different story. And in these poles, for instance, they become infinite, and that's not very good. But I'll get back to that. I will just mention this one tool, which is fantastic. Poincaré studied this more than a century ago, and he plotted this by looking at the trace of this A matrix and the determinant of this A matrix we talked about before. And here you can see in visualization how if the trace becomes negative, then you sink, you kind of collapse it, and if it's positive, you expand. And similarly, if the determinant then becomes larger, then you start spiraling in different ways. And the stability understanding here gets a very specific meaning, because stability here just means you stay in the neighborhood. If you start to move out of the neighborhood, then stability is no longer guaranteed, because we can't ensure that things don't grow out of bounds, for instance. And here is a very cool example, is the harmonic oscillator, which is basically known as a spring. So here is the dynamical system equation for it. I'll just show what happens in the plot, because I think it's a bit more intuitive. Here you have a spring, it goes up and down. And so that's really the physical model, if you will. But we have to model the state with two different variables. One is the position, of course, it goes up and down. Right, you can see that here on the y-axis. But the velocity is a different thing, because you can see the velocity actually changes in a positive and negative sense. And so that's a property of this state that we have to measure. And it's a really nice plot to show in phase space. You can see it looks very clean. And you can imagine what happened if you dampened this. The velocity would slow and the position would slow, so it would slowly spiral inwards. Right? That's what happened when you get this spiraling effect. And you can dampen this, as I said, and you get this phase plot, right? So you can see, okay, it's a GIF, I can't stop. But you can see that in the beginning you have these trajectories, and they will slowly spiral inwards. What it's showing here is what you can then do with changing some of these parameters. And I think it gives you a very good intuition for the phase portrait. You can see how the ellipse or the circle changes and suddenly stops becoming an ellipse. And you can look at the poles we talked about before, and you can look at the stability in this Poincaré plot we talked about before. I know there's a lot of information. I'll just dump this here, because I think the takeaway message is that phase portraits and Poincaré plots are great ways to gain intuition. It helps you understand and visualize geometrically what's happening.
Jens, question.
Yeah.
Yeah.
What do you do when you have more than 3 dimensions?
That's a good question. You can't do the same, right? So you'd have to either pick some variables that you like, or grow a bigger brain. I mean, at least these portraits won't make much sense. Right? Yeah. So, yeah. This is not a perfect method, and I have a lot of caveats. I'll get back to that in a second. But I will just introduce another very cool idea, which we touched upon but didn't use words for. It's attractors, and it's exactly what you think it is. It's just region in space that attract trajectories, and this should become obvious when we talk about these phase portraits, because if you're fixed somewhere, that means it won't move. So when you land somewhere, you can imagine you're in equilibrium. You're in a perfect space where you're not going to move. But you can also imagine that the orbit or the stuff doesn't stay fixed, but it cycles in some kind of period. And then, of course, you have very weird fractal structures that's known as strange attractors, which I won't talk much about. But all of these concepts in terms of attractors and limit cycles and orbits are very important in biology because they're known to be associated with stuff like memories and rhythmic behaviors. We talked about these oscillators before, for instance. So extremely important concepts. And Van der Pol is actually one of these attractors. Like it has this, you can see it loops around basically. No matter where you start, you end up in this kind of cycle, roughly. Almost no matter where you start. And that's known as basement of attraction. If you have a set of initial conditions that lead to the same attractor, then you have this basin essentially. You can think about it as a convex surface where you end up in the bottom of the bowl. And that's also very important for neurocomputation. That's basically what Hopfield memories are doing, right? They ensure that you land up in a certain pattern. And much more can be said about this. Storgatz drives this point home about importance of geometry. So I just want to read you a quote because I really like Storgatz as a guy, but I also think he nails the argument here, right? We could look at it analytically, but there has to be a better way, or there ought to be a better way. Like if you have a system, you want to draw the trajectories and extract information about the solutions, right? That's exactly what the phase portraits and these kind of methods are about. We want to look at the system and immediately understand what's happening. That's very difficult if you don't have these tools. And as I said, there's a lot of caveats, and nonlinear systems are a completely different story, which I'm not going to go into. I'll just say that Storgatz has this very, very nice plot, which says that the more variables you have, and the more nonlinear they are, so to speak, the more unknown they are. And if you look at it, on the lower right here, we have stuff like waves and plasmas and epilepsy and neural networks. So we're kind of out of luck. But that's also why I think dynamical systems are so important, because they're really the frontier of our standing. Our toolbox is just not as developed. I'll just mention a few extra keywords for this kind of understanding, like Laplace transforms, I think are really awesome tools as well for frequency domain analysis. Stuff can bifurcate, like if you have certain initial conditions, it might at some point be that they can end up in two different trajectories in your phase space. Poincare, we talked about. Of course, you can have stochasticity. And then statistical physics is very cool to look at some of the energy-based models. Again, Hopfield network is an important point. I'll just mention some of these attractor networks and neural networks, just for you to get an understanding of where this is important. We talked about central pattern generators, decision circuits, right? Winner-take-all dynamics. If you have some kind of binary decision, right? At some point, for instance, my motor command from a motor cortex has to win over all the other candidates, right? So then you need some kind of decision circuit that can then discretize the solution. So what's important, I think, is that this is a very, very nice way. I mean, attractors is a nice way to create robustness despite having a lot of noise and uncertainty. Good. I want to highlight this very cool example from 1991, which is by Ostrom, who's a very known control theory guy, and Carver Mead, actually, who sat down and studied what we can do with a single neuron. And what you see here is then the velocity of the system over time. So this is then, you can see basically a plot of the state space over time. And here you're controlling some signal. And this is just a single neuron that you use as a servo mechanism. And you can see it does relatively well. So this is a really cool study of how we don't need complicated digital machines. We just need a single analog neuron, and we kind of solve the neural servo problem. And I think this is a very good example of why biology is so good at this. I think this is exactly why biology was designed. I'm not the only one saying this, but that's why we should study this. So let's move on to neural network dynamics, because obviously we don't just want to look at artificial systems, we want to look at neural network systems. So I want to have a very brief aside to explain the adjoint method for backpropagation. Again, I go through this very briefly. Please ask questions. It's a little bit hairy mathematically, but the intuition, I hope, is relatively easy because we're somehow stuck computing gradients through some of these differential equations because we have solvers to get analytical solutions for them, but they're very heavy. And to do it efficiently is difficult. So instead of doing it forward, we can use the adjoint integral, where we are basically computing backwards in time. And we're using some kind of adjoint state here, which you can say that it keeps track of the credit across the system, right? So we're taking the partial of some kind of function that could be our neural network with respect to some parameters in some state, time, and parameters. And of course, we want to differentiate that with respect to the laws. We want to see what's the contribution of this network over time. And a very nice way to visualize it is that each state at each individual point in time contributes to this loss somehow. And we could do a full backpropagation through time. That's very costly. So we just take this adjoint state variable and flow it backwards in time. So we can basically at different times in the timeline here use this credit assignment, if you will, from the adjoint state backwards. And that gives us the exact solution. And the reason I mention that is because in 2019, there was a really cool paper that talked about neural ODEs, where you can parameterize the derivative. And the way to think about it is that we're basically allowing infinite layers. So we're basically having some kind of neural network with parameters theta, and then you can use the adjoint method to solve this. And the way to visualize this, I think, is very, very cool because you kind of know these phase portraits by now, is that you can imagine a residual network with fixed depth. But what if you then allow the depth to be continuous? You suddenly get this flow field. And that amends itself for optimization mechanisms. You can get a much more granular and interesting look at this stuff. So again, the adjoint is a little bit hairy, but I think the insight here is very cool. Our neural network becomes essentially an ODE, or we can do optimization on this ODE. And I mention that because Wunderlich and Piele put out a really cool paper in 2020 that they called EventProp, which is essentially bridging this continuous and event-driven computation, because where Chen et al. Here was looking at conventional residual networks, we are working with spikes and these differential systems. So look at a leaky integrated fire, for instance, you have some kind of hybrid system where you have this dynamical system until a discrete event appears, but you can actually use the adjoint method, what they're doing here, to then solve the optimization problem. So you can get exact gradients for these systems with very cheap memory, and so that's something I'm very excited about. I think it's a very cool direction, and I know that, for instance, the group in Sussex is working heavily with this. With Thomas Novotny, if you're interested. Another thing I'll mention is group symmetries. And this is a little basic, probably also a little hairy math, but you probably know this from your calculus. Like, you know that you can decompose systems by linear combination. So if you have some kind of system, you can kind of choose some bases here that describe your linear system with, for instance, something like orthogonal polynomials. And what's really cool here is that you can use harmonic analysis to do this. So instead of choosing, for instance, linear bases, you can have like complex periodic functions like sine and cosine. And this is exactly what happens in the Fourier analysis, for instance, that you're probably familiar with. And this can capture a lot of different actions on your space. So if you're working with some kind of group, some kind of set of operations. You can think about rotation, translation, scalings, and you can capture this with this kind of linear combination. It's not going to be perfect. You're going to have artifacts, but it's going to be an approximation. And the Legendre polynomial here, for instance, is a very good example because it's actually the optimal approximation in certain conditions. So it's complete. You can use any function to expand it, and it's optimal in L2, and you can kind of you can compute it relatively efficiently because it's basically a linear operation. So there's a very cool paper from 2020 that you probably heard about before. If not, you should really go bother Michael about it. He knows much more about it, and Terry as well. He's online. And the cool point, sorry.
And also Nicole is quite expert in this stuff.
Ah, Nicole there. Yes, definitely. I mean, I guess, Nicole, you touched on this also in your talk probably. No, not about VS8, sorry. Anyway, but if you think about these polynomials, you can kind of plot them here, and here's just for the units here, we have the time here as theta. Again, a confusing notation, I apologize, blame the paper. But essentially, you can look at how the different bases in the polynomial change. And if you combine them linearly, you get this approximation we talked about, and that can be done in linear time. Hippo took this further. Oh, sorry, this disappears. And I don't have time to explain this in detail, but it's very cool because you can use some of these projections to get a very cool continuous time memory model, which allows you to do very efficient learning if you initialize your matrices correct in your state space models. And that's basically, I think, the basis more or less for the SSM story. I think my slide is a little overflowing here, but you get the point. This is, I think, a wonderful way to look at dynamical systems in neural networks. We can look at this. We can look at the dynamics as a continuous time evolving system. We can use that insight to encode it in a suboptimal representation, like a polynomial projection. It's not perfect, but it's going to be good enough. And then we can use that in our dynamical system and initialize our matrix accordingly, for instance, with the polynomial bases to get very, very good results. And that's pretty much what's happening in the SSM space. And Steve, I saw you linked your SSM talk before. I think you also covered this there, right? So go and check that. Steve knows a lot more about this as well. Another thing related to dynamics is spectral analysis, because
Yeah, I have a question.
Mhm.
So the are the Legendre polynomials, are we approximating the function in phase space, or are we approximating something else?
Well, so the in these, so it's all about finding a good matrix representation. Essentially, we want to describe, like, we want to describe what happens when you predict the dynamic. That's essentially what the matrices here are doing, right? They're applying some kind of factor across your variables to each component in the state in the input, for instance. So the Chandra polynomial is used to decompose or find different coefficients for all the bases that best approximate whatever you're describing. Was that a good answer? Does that make sense?
Yeah.
So maybe an example is in order. Sorry, I can't hear you well, I think.
No, I think that's okay. Thank you.
Yeah, Terry is writing, it's in his own space. Phase space would be if we are doing the same thing, but using sine and cosine instead of the Legendre polynomials. So it's its own Legendre space representation, if you will.
Awesome.
Yeah, I hope that. I mean, I'm going to be online as well, so feel free to ask me questions also in the next following days. Although I loved the interjection, please ask questions. That's why I'm here, right? I'm not here to talk you to death, only partly. And I realize I'm the only thing stopping you from enjoying your Saturday off. So I'll crack on with it. Okay, I just want to mention this very, very cool point, because now that we can study we can study this kind of decomposition. It turns out that spectral analysis and frequency domain analysis are really cool for revealing some kind of dynamics we can exploit. So namely symmetries that might exist that our models would benefit from learning. That's basically what happens in physics, right? That means physics is all about symmetries and invariance. So if we look at this from a spectral point of view, the parameters could oscillate in a certain way that it exhibits certain geometries. That's symmetries we can exploit. The harmonic modes will then have different parameters with different frequencies, and we can basically use that to learn certain certain known patterns. And there's a very, very, very cool paper by Giovanni Macetti from 2024 that talks about how a neural network can learn certain symmetries or invariants in circular harmonics. So that's just one type of harmonics, but you can have other harmonics without knowing the structure or the geometries beforehand. And that's a novel finding. We didn't know, given a system we weren't aware of beforehand, we wouldn't be able to learn it. And I think that's very exciting because we are faced with a lot of systems we don't know, but somehow we still learn them, right? I mean, babies still learn to walk without, I think, having a preprint of how walking works. And so this kind of spectral analysis is not just good for SSMs. It's a really interesting thing to study geometric structures like symmetries and invariants that we can learn and use in neural networks. I'll just leave this here. I think it's one of the coolest papers I've ever written or read. And I'll move on briefly to talk a bit about, I'll spend the next few minutes just very briefly going through some of the work that I have been doing. It relies on the spike response model. So now we're departing from the spectral idea and into, but still talking about geometries. And the spike response model is a very cool way to look at neuron dynamics. And instead of having neuron dynamics, it's very, very complicated nonlinear system, they're composing linear kernels. So if you imagine a spike model working with some kind of integrator, that's a linear kernel, kappa. At some point, that output here gets sent to a heaviside function, and if you reach the threshold, you spike. Of course, there's a spike output from that system, but there's also a reset kernel that then kills some of the signal, goes back to the reset potential, and continues integrating. And so these are all linear kernels, and since by now we're familiar with linear kernels, we can understand and use them. And some of the work that I've been doing is to study geometric representations and preserving transformations. And the reason why that's important is because we see a lot of signals coming in at, for instance, different transformations. So like if you look at something visually, like this number 2, it can be scaled. I can be very close to it or very far from it, but I still want the same understanding of it. And the same thing goes for time, right? If I'm looking at something that goes very slowly, very quickly, I should still give a same or similar understanding of that signal. And it's very difficult for me to visualize this because not just becomes spatial, it also becomes temporal. But we want spatial temporal covariance. So what I've tried to do here is to imagine some kind of square that gets scaled up, right? So imagine this is time and your x-axis here, and then it slowly scales up. And you can do that very slowly, or you can scale it faster. And the quicker you scale it, the bigger the square becomes. And invariance then would be that you get a similar response to that scale at different temporal scales. So we're looking at the different spatial scales, and we get similar response over time. And that's basically what we're seeing here. So the brief story here is that we can use neurons to then represent different time scales and capture similar signals. Of course, there's some pixelation effect here, but the point is that just like we want to preserve different scales in space, we want to preserve different scales in time. And the reason why that is important is because that's exactly the geometrical structure and the symmetry we talked about before in the spectral analysis. There's a group structure we want to learn. And what's really cool is that it lets us algebraize, if you will, structurize and compute on geometries instead. That's similar to the Strogatz argument before, because geometries is they're a very nice way to get intuition about some very complex dynamical systems. And the immediate implication is that we get a very smooth neural state space. So we no longer stuck with a unknown model. We have a model that we can permute. It may not be perfect, but we can start exploring it and learning it. They're covariant, so they're structure preserving, which means that if you change something in our parameter space, it has a very concrete meaning in our dynamical system space. And they're symmetric, so we can start to understand transformations as group actions. So groups are basically just think about them as a certain set of actions that apply. Like a rotation can only happen in a certain circle. Otherwise, you can't rotate more than 360 degrees, and it kind of stops. It starts to count at 0. But the point here is that it becomes differentiable. And I can talk much more about this, but I just wanted to show you that understanding these dynamical systems as a geometric process has immense power, I think, and is very useful for both, deep learning in general, but definitely also for instance, control and predictions. So I think there's something to be said here about bridging biology and AI. Like we want to understand computation, these state-based formalisms. We also want to understand temporal dynamics because it turns out that the brain and physics are temporal systems, so we need to be able to describe time. That's also what neural systems are very good at. There are actually interesting enough benchmarks to show that neuromorphic computing is pretty stupid unless you use time and sparsity. Otherwise, you might as well just use a GPU and be done with it. It lets us do hierarchical processing because we can understand these signals at different scales. And we can start to understand something like adaptive behavior because we can latch on to these symmetries. We can latch on to these structures that we know a priori maybe might exist. So I'm very excited for neuromorphic hardware because they can implement these things. They're exactly neurons. We can describe these covariance properties in neurons. And I think this SSM-like, this decomposition, this spectral analysis story that is basically used in SSMs are incredibly exciting because that's exactly the dynamical system. So I've gone a little bit over time, so I'll just very quickly iterate. I will just mention the neuromorphic intermediate representation because that's also using dynamical systems. Which by the way was invented at Telluride a couple of years ago, but that's a representation that captures some of these computational primitives. Steve knows a lot more about it, so hit him up. But we talked about observability, we talked about controllability, we talked about stability. If you want to fly airplanes, you don't want them to crash. And we talked about optimality. All these are, we just cursory glance at them now. There's much more to be done. So I'm very excited about hybrid systems, learning dynamics. I'm very excited about Koopman operators, like the talk given the other day, because you can linearize some of these nonlinear systems. Again, it's not the same. And it has very, very nice segues into VSAs, which Nicole will know everything about. With that, I think I'll just conclude and say that dynamical systems are very, very difficult. I think it's a huge topic, but I think it's very important. And I'm really, really happy to be talking about it today. And I look forward to interacting with you guys throughout the workshop. Thank you so much for your attention. You survived.